Yeah. A very warm welcome to all distinguished guests, respected faculty members, industry professionals, and our enthusiastic student participants. Before we begin, we would like to introduce ourselves. I'm Satishi, and this is my co-anchor Rishi. We are students from AIT department, and we are very honored to be your host for today's program.
On behalf of the Indian Institute of Technology and the Center of Excellence in Artificial Intelligence and Cybersecurity, we are delighted to welcome you all to QiskitLab Area hands-on quantum programming experience. To mark the formal beginning of today's event, we will proceed with the traditional lighting of the lamp, a symbol of knowledge, purity, and enlightenment.
We request our esteemed guests, our respected Chairman Dr. Sundar sir, Principal Dr. Rajesh sir, Dean of Research Dr. Surendra F.G. sir, HOD Dr. Devi Kannan, along with all the deans and heads of various departments, and today's distinguished speaker, Mr. Jay Kumar Tarikati sir, to kindly come forward and light the lamp.
Thank you, dignitaries, for taking the occasion to your presence and lighting the lamp of knowledge. As a gesture of respect and in support of our opening initiative, we now invite our guests to receive samples, a symbol of growth, sustainability, and new beginnings. First, Dr. Sundaraju sir, the founder of Atria University and the chairman of Atria Group, a visionary leader who continues to guide our institution. We request our principal, Dr. Rajesha S. sir, to kindly present a token of appreciation. Thank you, sir.
Next, Mr. Jay Kumar Tatipati sir, an industry expert from Quant Curious Technologies with deep expertise in quantum system. We request our chairman sir to kindly present a token of appreciation. Thank you, sir. Our remaining distinguished speakers, Mr. Aryav Mishra, research engineer at IBM Quantum, and Ms. Janani A, researcher from IBM Quantum and IISER Pune, will be joining us later as per the session timings. To present the detailed agenda for the day, I now invite Mr. Gautam S. Sir, our program coordinator, to deliver the main briefing.
So good morning, Amara. So before we proceed, here we brief our today's program. Participants will be introduced to core quantum concepts, engage in quantum circuit buildings, explore QiskitLab primitives, and take a part in applied session on variational quantum algorithms. The workshop is designed to provide a strong conceptual base along with the essential practical skills. So in quantum, there are so many sessions have been conducted on further premises, and this is the base step where we are going to learn with respect to Qiskit programming language. And there are series of projects or case-based studies will be organizing with our CoEs, and even you can be part of this Qiskit programming as quantum computing application applied programs. So thank you one and all present over here.
Thank you, sir, for presenting the agenda and giving us a clear overview of the day. Now, the welcome gathering will be officially delivered by our respected chairman, Dr. Sundaraju sir. His continued guidance and steadfast support have played a vital role in strengthening our institution. His dedication to fostering innovation and academic growth has always encouraged us. Sir, we request you to grace the viewers.
Thank you. Morning, everyone.
Good morning, sir.
I think if there's ever a time when one said, let there be light and never light the lamp, today is one of those days. Because quantum technologies is really, I would say, it's not even in its infancy. It still has to take birth, if you will. So the real challenge for us is to say, who will help us travel this journey of learning this thing, animal called quantum technologies, quantum computing, and it seems to me that you will most probably be the pioneers in that area if you devote the time and effort required in this space. Fortunately, there's unfortunately is the wrong word for it. When you're pioneers, you have to be self-driven. And then presuming that the fact that we are here early in the morning and saying, what is it that we can, ATF can help us move along in this journey of quantum technologies, does mean that you are driven, you're driven internally, if you will, and hopefully, I'm hoping that if we look back, maybe even have another meeting a year from now, enough of you, if not all of you, would have traveled this journey to say, I am now ready to be a true contributor to the nation's journey of quantum technologies. I've spent no more than 5 minutes with Mr. Jay Kumar, and I already feel like I know more than most people in quantum technologies. That's, and the point that I'm making is, it's that much of an infant state in terms of people understanding what it means. I think there's a little bit of understanding thanks to US and China showing us what can be done and the disruptions that we can make happen when you leverage quantum technologies. Between AI and quantum technology, I think there's a whole lot of new world disruption journey that happens. You are from, I mean, ATL is an academic institution, and I'm hoping that quite a few of you are from other academic institutions. And I'm hoping that you will be the leaders in making the next generation of young adults quantum familiar and quantum user natives, if you will. I now am engaged in the AI space, and I keep this hearing this quantum, and Karnataka government has decided that AI is a major space team, and in that team, we have patrons, such as say, like, from the ITBT ministry and the skilling ministry, who are engaged to figure out how to make sure that the next generation of young adults are not left behind. And they're trying to create a program. As a matter of fact, later in the day, I have an engagement with the Vice Chancellor to see what can be done ahead of, beyond what is being done as regular curriculum, and how do you ingrain this new animal, if you will, called AI and the concept technologies across the board. And these are technologies that are not like a, you siloed things like CS, IS, and mechanical and civil. These are foundational things that cross all barriers, if you will. They are not, you know, amenable to be siloed. While there will be siloed application, I think the interdisciplinariness that is required, AI and quantum technologies along with semiconductor technologies, I think, will be foundational, and if you look 5 years from now, will be all pervasive in all spaces. How much or what is the speed at which we make that happen is really dependent on groups like you across the country that are engaged in pushing the envelope, or actually starting the envelope, but taking it all the way to, saying we're pushing the envelope to a point where the country is well laid in terms of foundation. We are behind. We are behind certainly China, certainly US. The thing is, can we quickly catch up with them, and hopefully, as peers, be able to engage with those kinds of environments to a point where India is looked upon as a resource center for these spaces. I'd like to think that because you have started today, you are going to be the leader in that space. The commitment that we show is what will determine whether we are really a country. And don't say this actually, as a country, we will be lockstep with the world. And I think this is a journey. To me, it sounds like an exciting journey. I hope all of you travel that journey, and if we meet up 2 or 3 years from now, some context, all of you are saying we are part of this pioneering group that is pushing the envelope in this space. Again, I wish you all the luck and the very best in terms of getting started. I keep telling people, inertia is the biggest thing to overcome. The fact that you're here, you move that needle on inertia, you go past that, I think this is a journey that all of us will be excited about, and I'm hoping that you will all be excited, and this is the start of the journey. And I'm asking the principal, let's not stop at this. How do we continue this engagement? How do we create groups, if you will, that is looking at some verticals to say, I'm here, but we travel till we get to that vertical and solve problems. I was talking a little earlier, there's a whole suite of areas. Health seems to be a big area, but it doesn't matter. From health to logistics to name what you will, there are verticals that can leverage these technologies. Pick a vertical, make sure that the foundation is robust, and pick a vertical and become an expert in that. Is my message to you, if you will. And I really hope that you will enjoy this journey and enjoy the journey as much as I would like to do. I mean, I've kind of committed. When I sit in places like this, I keep saying, I wish I was a little younger and traveling this journey to make sure that these exciting. And I can be very honest. Today's disruptive age is a disruptive age, and there are technologies of various spaces that are coming that will disrupt. If I look at, and I like to do regression analysis and figure out what the future holds. And my belief is 2035, the world will be a different, really different world. And it's really left to people like you to make sure that India stays pace of the change or disruption that is happening in the world. Again, the very best world. Thank you.
Thank you, sir, for your warm and motivating words. We extend our heartfelt thanks to our Chairman, sir, Dr. Sundaraju, sir, Principal Dr. Rajesh Ayas, sir, Dean of Research, Dr. Surendra H.G., sir, HOD, Dr. Devi Kannan, ma'am, along with all our deans and head of various departments and the entire faculty team whose constant encouragement and vision have made this event possible. A special appreciation to our coordinators, Dr. P.B. Pradeep Kumar sir and Mr. Gautam R. sir, for conceptualizing and organizing this impactful program. Yeah.
It is now our privilege to welcome our first speaker of the day, Mr. Jaikumar Tanisar, from Quantorius Technologies Private Limited, an expert greatly respected in the quantum ecosystem. He will be leading the first session, titled Foundations of Quantum Machine Learning. With extensive industry experience in quantum technologies, he brings valuable insights into the future of excellent computation. Sir, we are honored to have you with us. The stage is yours.
Hello, 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 hello. Okay. First, I would like to introduce myself. I am Jay Kumar from QuantQueries Technologies Private Limited. Before working here, I worked as a software engineer for 22 years, out of which I have 8 years of experience, both including my learning session in quantum computers. Before embarking my journey into quantum technologies, I worked in IBM as well as in HTC Global Services. In my quantum journey started in 2017 and it will be going in future also. Now I will go into the actual session today, and I hope all of you are already introduced to at least the quantum fundamentals or quantum phenomena, as well as at least all of you has some knowledge in linear algebra as well as in Python programming. I assume that. With that assumption, also I assume that all of you are having some knowledge in machine learning. Okay, what is machine learning and what are the different? Anyhow, we will revisit those concepts not in detail but outlook only. After that, the main agenda of this session is first we will see what are the different types of machine learning schemes. Then you will be introduced to the few quantum phenomena that are predominantly used in quantum machine learning. And after that, we will go into the circuit related or components of that QML circuits. How, starting from how your classical data is converted into the quantum state and different types of schemes available in to do that one. After that, how, where actual processing will happen and different types of processing circuit. That is generally used in normal computers, in normal algorithms, sorting algorithm. How I will implement it in quantum program by using the operators. Also, I will show you the different types of encoding principles that we will discuss in this class. Now, finally, I will show you one application of this QML where that is where we will use in optimization of our portfolio with the 10 stocks, and we will see how it will be done. Okay. Now we will start with the actual thing. This is the classical learning machine. In classical learning, what is actually in artificial intelligence, classical learning, machine learning is one of the subset of the artificial intelligence branch. In that, what it will do, it focuses on segregating or identifying the patterns based on the data within the provided data. And the whole classical and these algorithms, developing these algorithms will generally use full mathematics, especially linear algebra. Okay. Then these are three types of these are three types of machine learning algorithms that are there, and one is the supervised learning, the second one is called the unsupervised learning, and the third one is the reinforcement learning. In the first one, what it will take, you might have known that in supervised learning, what they will do, you will be provided with the data with labeled data, and based on that your algorithm will learn. There will be one evaluator who will evaluate the algorithm, and once evaluation is done, it will be tested on the training data set, and finally if algorithm works in the optimized as per our expectation, then it will be deployed into the production case. And in unsupervised learning, there will not be an evaluator. The algorithm will itself learn from unlabeled data sets and identify the patterns. But when it comes to in the reinforcement learning, what it will do, reinforcement learning algorithms are mainly used for live in real-time environment like traffic, even in predicting the stock market, prediction of a price of a stock based on the evaluating the content. And reinforcement algorithms are mainly used in our self-autonomous vehicles as well as in robotic, in healthcare, in robotic operations generally. Last month, I think, in Apollo Hospital has done successful operation using reinforcement algorithms. In Chennai, they have done. And these are the graphical representation of all these three types of learning machine learning algorithms. Okay. This is just an introduction. Now we will enter into the basics of quantum mechanics or quantum principles that is being used for programming or your quantum programs. Actually, the main phenomena that are being used here is one is superposition, and the second one is called the entanglement concept, and the third one is called interference. These are not the only three properties. There are quantum tunneling and quantum black hole. Here in QML, these are the main three principles that are predominantly used. What is meant by superposition? Here in before going into the superposition, let us see let us know how the data is being manipulated in the normal computers. Actually, what are the object we are passing into the normal computer, what it will be converted into zeros and ones. only a bit, strings of bits. That means 0, 1, 0, like that it will be converted. After processing the data, you will get the output also in the bits of string. Before presenting into this one, it will again that the bits of string is being converted into the type of the input. That means here in quantum computer, they will use somewhat called the concept called qubits. Qubit is an analogous to the bits. It will be represented in the form of vectors, not a bit of strings. It will be used in the form of vectors, and to manipulate these vectors, we will use the operators. And there are several different types of operators, and few of them are unitary operator, Hamiltonian operators, and measurement operators. Measurement operators is used to extract the information from the qubit state. That is how it is done. And apart from the qubit, apart from exhibiting the zeros and ones, the qubit can be in a superposition state, means that is, it is a linear combination of the basis states. Basis states in our case is zeros and ones. That is the superposition. That means at a point, suppose if you want to learn, suppose if you take a coin, when you normal computers, what it will do, if you toss a coin, means after hitting and landing in the ground, whatever the head, either head or tail, only those states will be processed. But in quantum computer, what it will do, if you toss a coin, means when it is spinning in the air, at that point of time they can gather the states and they can process the data. Because when it is spinning in the coin is spinning in the air, it exhibits simultaneously both head and tail at a time. That means the probability of changes, it keeps on changing until it hits the ground. Once it hits the ground, means then that probability changes to the deterministic value. That means either head or tail will be available on the ground when it hits the ground, but when it is spinning in the air, it keeps on changing. That is called the superposition. And the entanglement concept is somewhat peculiar to this in this quantum mechanics. Entanglement means, suppose actually in quantum mechanics, it studies the phenomena or properties of a subatomic particles which keeps on changing. With respect to time, it keeps on changing. It exhibits different characters at different point of time. So here in entanglement, what it will happen means, if you merge, if you add two subatomic particles, after merging, and if you separate these two are subatomic particles somewhere, and it will be in somewhere very, very large distance, separated by large distance, means by studying the nearest subatomic particle, you can evaluate the properties that are there in the far distant particle. That is called entanglement property. If you change by applying the operations, if you change the states of this nearest subatomic particles, the same properties will be exhibited at the distant particles. That is called the entanglement concept. And the third one is the interference. This one, all these three things will be used, but here interference means, here what it will happen, we know that waves in class 11th we have learned that waves exhibit in the form of cosines and sines, right? And by using those that phases, that means sin theta is the phase. By using the phase, we can either increase the value of that wave value or decrease the wave value. If this by increasing the if the same waves are in the same phases, again that theta values will phases are evaluated in the form of thetas, that means in the form of radians. If when two waves, if you have two waves and those two waves have the same value of theta, we say that they are in phase, and these in phase waves are being used for constructive interference, and if they are out of phase, we are used for destructive purpose, destructive interference. This, since machine learning, if we need to increase some values and we need to negate the other values, means we will use this constructive and destructive interference a lot in machine learning and in QML. Any doubts? This is the architecture of the quantum computer. Actually, in the left side, this one is the data center where your data will be there, and this is the quantum processor where actual processing will happen. And this processor is being shielded with the chamber. That means, because why it is being shielded, even a small minute change in ambience will have a huge impact on the performance of your circuits. So it will be cooled by cryogenic refrigeration unit, and from data will flow from data center through your classical data, and it will come here inside this one. Here it will be the processor, and it will be written back to the data center. And here is the place where your actual classical data is converted into the quantum states. Data will be read in the form, in quantum circuits or in quantum programs, data will be read in the form of states only. That means in the form of vectors. It will not take a scalar quantity at all. Here it will be changed. Once it is processed here, then again here the output from the quantum circuit will be in the form of, again in the form of vectors only. Those vectors will be converted back into the classical data, that means in the form of zeros and ones. They are in analog circuit converters. This is how the architecture of a quantum computer. Now, actually the quantum circuit mainly consists of the qubits, and the operations are performed using the gates. These gates are unitary in nature. That means, what is meant by unitary? What is a unitary matrix? Madam? No, madam, that is identity matrix. Unitary matrix, if you take the dagger, U dagger, and if you get if it is equal to the inverse of itself, then it is called the unitary matrix. U dagger means you will perform two operations. Again, here in all the matrices or quantum states will not be in real numbers. It can be a complex numbers also. Okay. If it is real numbers, means U dagger means changing the dagger means you need to apply two operations. One is the taking the transpose of a matrix, and if there is any complex number inside the matrix, means you need to perform conjugate of that matrix. Combine doing the same two operations at a time, we will call it as a dagger or self-adjoint operator. Okay, and matrices will manipulate. Madam, suppose if you have 1 A plus BI 0 C plus DI, in diagonal you will be having elements. Suppose it need not be a diagonal, your entire matrix can contain any numbers. Okay, suppose if A plus BI is the first element and C plus DI is the last element, is in a 2 by 2 matrix. First, what you can, U dagger means, or dagger of this matrix means, first you take any operation, you can perform the complex conjugate. That means first A plus BI becomes A minus BI, and this C plus DI becomes C minus DI. Then you do the transpose. That means changing rows into columns and columns into rows. That is called the unitary matrix. If that resultant U dagger becomes your inverse matrix means, then we will call it as unitary matrix. That is, and by nature all the operators in quantum circuits must be unitary in nature. Okay. Now, after that, by performing or by applying the gates, and you modify, you manipulate your quantum state, your output will be also be in the form of vectors only. That means in the form of state vector. So, to extract the value, actually we need some scalar value, right? To extract that one, you need to perform measurement. That means all the quantum mechanics will work on the mainly in one used mathematical framework is this one, what, linear algebra. And in normal convention method, in normal laptop, you don't have any measurement type of concept. Here, to extract the data, you need to apply the measurement operator. That is the only thing. That is the main thing. There we will use the digital circuits or analog circuits. Here we will use the quantum circuits, means linear algebra. And this is the QM, that is the main how the quantum circuit will be. Actually, I should have shown you one circuit. I will show you the before conclusion of this. And in QML, what it will do, actually if you want to perform, if you want to do some machine learning programs, means if you suppose if you want to if you want to do some machine learning operations on medical data, say some chemography or some other MRI scans, if you want, it is the size, I mean to process the image, it will take so much of time. It must be converted into RGB, and it will be in the form of matrices. To manipulate these matrices, you need enormous amount of computer resources, right? To overcome this one, we will use all this QML, all the computational part we will deploy, we will make use by, we will perform on the quantum computer. But for optimization purpose, we will use this normal conventional lab computers, so that it will become a hybrid circuits. Okay, this is how we will do it. In QML, actually it is a hybrid circuit. We will make use of both the computational power of quantum computer as well as our normal computer, classical computers. And to program this one, actually there are 7, even many, predominantly we are using, there are 7 types of programming frameworks, in which, out of which Qiskit is the front runner. And almost all these programming frameworks are developed in Python language, except Microsoft's Q#. Q# is written on C# language, and Kirk is the Google's product. Qiskit is IBM's product, and there is one more bracket SDK, software development kit, that is Amazon's product, and the Penny Line is developed by John Doe company. This Penny Line is extensively use it for QML problems. To solve the QML problems, we are using this one. It does not mean that remaining we are not doing. Qiskit is also, we can use Qiskit also, but many industry we are using this one. And the beauty of this one is, from once you learn this penny line, you can develop your penny line the program, and directly you can run it on your quantum hardware, I mean IBM hardware. And penny line is also developed in Python only. This is the paradigm how it will do. Suppose if you have 7 bits of number, so that before coming into your classical algorithm, that will be converted into zeros and ones, bits of strings, and here once that is processing is done, you will be given the output in the form of bits of string, and again internally it will be converted into your normal decimal numbers. But here in 7 qubit, the same 7 qubit, what it will do here, what the state, these 7 qubits will be changed into, will have different types of, will be taken into the different types of combinations, and you will get 2 to the power of 7, that means almost 4 4 16 56 128, 2 to the power of 128 states are developed at a single time, and the entire 2 to the power of 7 128 states will be fed into the quantum algorithm. Here, because of this parallelism, we can computations performing, calculating or manipulating the states will happen very, very fast when compared to the classical thing. And this entire, before, what it will do, for every state there is one gate called Hadamard gate, that for every qubit, if suppose if for zeros, 7 zeros are there, for every zero that if you apply that Hadamard gate, means it will be shown into the, it will be converted into the superposition state. Similarly, every state will be 2 to the power of 72 states will be converted into a superposition state, and that will be fed into the quantum computer or into your algorithm, and parallelly every state will be evaluated parallelly, and you will get in the form of, you will not get the deterministic value, again you will get in the form of vectors only, where by performing or by employing your measurement operator, which data, which feature you want, that operator or Hamiltonian operator corresponding to that particular feature you need to apply and extract the relevant data. This is the comparison how it will be between classical and quantum. And the thing is, the beauty of this one is, since the circuits are reversible circuits, that means once we get in normal computers, what if is fed data, means once processing is done, means you cannot retrieve the input data, what you have done, what you have supplied. But here, because of unitary in nature, you can extract, you can preserve the input state also, but it will come at cost. But for that you need to use some auxiliary qubits in your circuit. Oh. Sir. Actually, this is first class for your quantum. Oh. Actually, this should be last session. I thought of having, at least you should. Yeah. Anyhow, in the next few sessions you come to know, so that you can apply reversible gates and you can retrieve all your You can reverse. Okay. Here, here this dagger symbol is this one. Just once, just like plus type. This one is the dagger. Actually, here if you take here I have given in the form of row. Actually, we will deal in column. To convert this one, I have given this one dagger. This A1 and A2 can be your scalars. It can be a digits. It can be a decimal number as well as complex numbers. And the question, the main thing is, and these vectors should be in normalized state. I think you should know what is meant by to. If you are given a vector, you are able to find the normalize. You cannot do normalization. This is the state such that both this vector should be in normalized state. Why? Because normalization will eliminate much of your computations. And this is for n greater than this. Here in classical thing, this will be a string of bits, but here it is a collection of vectors. And each A1, A2, A3 also, these are all called the features. Suppose if you have a record of 100 records, within a file if you have 100 records, and for each row corresponds to one record, and within for each record, it corresponds to, you are having different types of features, and those features are called A1, A2, A3, and so on. Okay, and again this must be normalized. And so, how will you do the approaches? That means, suppose you are having data will be there in the form, since we are data, you are having the in normal you are having classical data, and again you are having the classical computer. Similarly, you are having quantum data and quantum processor. Then these are all the different ways how can we process it. One is CC stands for your data is classical data, and you are processing the classical data on the classical computer. That means you are having classical, it is just like a typical classical machine learning algorithm. You are developing your algorithm that is taking classical data, and you are running that classical algorithm and by taking the classical data on the classical computer. That you can do like this in these two forms. And here what it is, you are having the quantum data, but you are running your classical data on a classical computer by using the quantum states or quantum data. This is QC, means classical data is processed on quantum computer, and this here QQ means both you are having quantum data, that means in the form of vectors, and those will be processed, you are having the quantum algorithm that is processed on the quantum processor. Here we are dealing with this one. This is normally what we are currently doing with. This is how it is. For classical approach, either your processor should be in CPUs and GPUs. Here we are in quantum computer, we are having QPUs, quantum processing units. This is CQ approach. I don't know. Yeah, but since you can do it. All this, but states is in the form of vectors only. What is NumPy? but it takes enormous of computational resources. Suppose if you, I will show you in the here one bubble sort algorithm. I will show you, because when I try to run the same algorithm here, yeah, I got memory is not because of computational resources you cannot perform, because it will be in the form of vectors. To manipulate vectors again you need to use matrices. That means to accommodate this both this it will take a large amount of CPU. Sorry, it's not CPU, this RAM. So you will obviously you will be getting some error. It will take some. This one is 32 GB RAM. I will show you also that one. And this is QC approach. Same algorithm, quantum algorithms processing the classical data. But here we are seeing only we are dealing with QQ approach only. This is QQ approach. Now this is the actual here. This is the what is meant by VQC, variational quantum circuits. VQC is variation. Actually, there are different types of algorithms. One is called VQC and VQE, variational quantum eigensolver, QAOA, quantum approximation and optimization problem. And I have taken this one. Here, what is same, everything will be same as per your classical one. But here, this is the circuit where actual computation will happen. Before this, there is one more layer will come here that we will see in the next slide. Okay. Here, what is all the your algorithm will be here, and the data will come into here. First, you will provide some theta is the parameter. First, by some value you provide, and it will calculate that data, and it will be sent for loss calculation of loss function. Then again, if it evaluates this loss function, then based on the expected and the actual one, here optimizer will change or take the value of theta. This is what it will happen in quantum computer also. Here, this is the one. Here, W key of theta is the place where actual things will happen, computation things. But this is the place, S of x is the place where your data conversion from classical to quantum states will happen. This conversion is called encoding. Encoding, data encoding or embedding. Once data is encoded, or that will be fed into the circuit. After that, here these measurement, these symbols will suggest the measurement operator. The output will be in the state of quantum state. From that quantum state, what this measurement will extract the information that will be fed to the classical computers, where actual evaluation will happen. Then based on the evaluation, it will take the parameter. Once the new parameter is tweaked, it will be fed to this. This part is called ANSATZ, ANSATZ. And this keeps on iteratively running till your algorithm works up to your expectations. And now we will see the inner details of different types of this encoding processes, as well as different types of ANSATZ available. This is components of quantum circuit. encoding layer will loads the data or converts the data into classical data into the quantum states and loads the data into your circuit. ANSYS is a template responsible for doing computations. Measurement operation extracts the information from the resultant quantum state.
So it uses encoding.
1 minute, ma'am.
Encoding and this measurement, these are not inside the classical computer.
No, madam. These three are only in the in quantum only.
External, the quantum computer. In that analog portion, where is the analog portion?
Analog here only, no.
Qubit portion and analog.
Qubit will be here only. Here it will come. This S of x will convert your data. That means zeros and ones in states, quantum states.
So it means it is a different circuit apart from this quantum, that qubits. Qubits will be.
Qubits is used for information representation. Just like zeros and ones, there we are using only zeros and ones. Here we are representing in the form of column vectors, that we call it as quantum states. And these generally we will call it as wires. These horizontal wires will represent the qubits. Madam?
Data is quantum, possible classical.
No, no.
Because you are given for quantum data and
Classical data. But here you are processing the data in Q only, no? So it will be QQ approach. Since here this is the part where that classical data is converted here. If the S of x is not there means, then it will be in QC. But here we are dealing with QQ approach only. Any doubts, madam? And we will see what are the different types of encoding processes available and different types of answers available. And one more thing, the performance of your algorithm will depend upon both these things. If your data is not good, that means if your quantum state is not good, means obviously your performance will be not up to the optimal. So you need lot of researches is going on in these areas. This is the components of quantum circuit, and this is called actually, here data is converted here. This one is called encoding layer, and for encoding we will call read-in protocols will be there. Read-in protocols. Similarly, once data is extracted from this quantum output quantum state, this one is called the readout protocols. So first we will see what is meant by read-in protocols. This is called data encoding class, or these are three terminologies that we will use, and it is converting the classical data into quantum data states, and it acts as a bridge between your classical and quantum algorithms. Okay. And these are all the different types. These are only few things. There are even more than this one, almost 22, 25 types of read-in protocols are there, out of which the first three are the basic one, and these are all somewhat complicated one. So we will see these three things now. This is why I told you, this the algorithm performance will depend on your reading, how your data is encoded. Why? Because suppose if you have say 1024, then if you convert into the bits means you will get some bits. How many? Suppose if my 2 by 2 may, or my data set is having 2 features, that means my quantum state will be in the form of 2 by 1 state, and to convert this one, every first one will be converted into zeros and ones, second feature will be converted into zeros and ones, and by combining this one, how many bits are there means those number of qubits it will be necessary. That means as your features in the data set increases means your number of qubits keeps on increasing. That is, both are directly proportional to each other. As the number of qubits increases, then your gates will have impact. Normally in quantum computers, they are very fragile. I told in the I showed in the architecture, the entire processor, quantum processor is insulated in the chamber, right? Any small change in the atmosphere will have a huge impact in this one. So the gates, if you run your, if you have say some 100 qubits of data, 100 qubits, that means you need to generate, you need to create the gates which can process all those 100 qubits. That means multi-qubit gates will because as the number of qubits increase, the gates, because of gates, there will be thermal radiations will be there, and it will change the properties of this processor, and it will not work at an expected rate. So because of encoding strategies, this has number of qubits will be have much impact. And thermal expressive power of the final model means one expressive model, one phenomenon that can change is your thermal power. If you run your laptop for 10 to 12 hours continuous means there will be heating, right? Similarly here also it can sustain up to some degree, but in quantum processor, even a small change in small electrical change or magnetic change in the surroundings have huge impact. So express power of the final model will be impacted very hugely. Now this is the base state, the first one. Here what you will do, your number will be converted into x1, x2 and so on will be your bits. Suppose if you are having 2, 4 in the vector, means 2 means 1 0 and 4 means what is meant by 4? You will get 1 0 0. Total how many qubits you need? You need 3 qubits. 2 plus 3, 5 qubits will be needed. And in basis, these are the normal zeros and ones. If you put in the form of this notation is called ket notation. Column vectors are given by ket notations. That means one vertical one, within that one you will give your data and followed by this right hand angle. This is called the ket, and the opposite of the ket is called the bra notation. That means bra, how will you get? By using the dagger notation, by performing the dagger or self adjoint operation, you will get the row notation or bra notation. This is how the for this classical bit information string of bits, this is the column representation. And this can be, if you have marker means I will show. Marker. Here 3 ones are there means we need 3 qubits. That means 3 horizontal rows. And to manipulate this data, you need a gate of 2 to the power of 3 by 2 to the power of 3. That means 8 by 8 matrix is needed to manipulate this state. Suppose if I add a Hadamard gate to this one and this one means, and how will you get from 2 qubit system, for single qubit system you can develop the 2 qubit system. From 2 and single qubit system you can develop the 3 qubit system by using the tensor product. It is just a mathematics, just a multiplication. Suppose if you have n qubit state means, suppose if there are n bits means you need 2 to the power of n by 2 to the power of n matrix or operator. Generally we will call it as an operator. And the state should be, if there are n bits means the state is to be, it's in the form of 2 to the power of n by 1 state. And this is one C naught gate. Here in NOT gate is there in analog circuits. Here we will use C naught gates. And C naught gate, suppose if there is actually a 40 hours class is there, only we can discuss with C naught gate. Only C naught gate. Suppose I will tell one small, suppose if there are n qubits means how many C naught gates you can create, you can have means it is n factorial. N factorial gates you can have. For single qubit gate, it is only one C naught gate. Sorry, for single qubit you don't have C naught gate. Only NOT gate is there. For 2 qubit gates, you will have 2 C naught gates. That means 2 factorial is 2 factorial. For 3 qubits, you will be having 3 factorial. 6 totally you will have 6 C naught gates. Like that you can. This is how. Here in basis encoding, once this is generally created by using the C naught gates only. Here if you see, if marker is there means, I will, sir, marker sir, okay. This is how, think it is not a, you can think it is as a circuit, quantum circuit. This generally while in normal programming, Java or C program, before initializing you need, before creating the variable you need to initialize that one, right? Say a equal to some value. Similarly here, before creating this one you need to initialize this one. Generally we will initialize all the qubits to get 0. That means 1 0. And these are all the gates. This one H is called the Hadamard gate. Walsh Hadamard had discovered, invented this one, so we will call it a Hadamard gate. And these are all the different types of multi-qubit C naught gates. And collection of in bits, collection of bits we will call it in classical computer what? Registers. Registers. Similarly, we call it as collection of qubits, we will call it as qubit register. Okay. Okay, we'll wait once marker will come, I will show just since it is a mathematics means by orally you cannot understand what this index qubit and what this value qubits are. Oh, okay, well, suppose if you see this, you just forget for this 0 0 0 0 0 1 0 1 1 0 0 1 1 0 1 0 1 0. These are all the data elements, features, and the position of this one is 0 0. Since why 0 0 means generally in for one qubit system at least you need to have two states. One is the quantum, one is the ket 0 and the second one is the ket 1. And here we are dealing with the zeros and ones, sorry, in the form of vectors. Suppose if a ket 0 is there, means only one qubit. Ket 0 means first one it will be pointing towards north pole, that means 1 0. Down ket 1 means 0 1. That is, and these are called the computational basis states. Computational basis states. Okay, again it will go into some inner depth. 1 minute. Those is thing. If you combine, if you do tensor product of these two 1 qubit systems, that means these two what we had just discussed, then you will get 4 elements will be there. 4 elements. And first element will be 0 0. That means 0th element. If you convert that to up to 4 means 0 1 2. 1. See this one 0 and 1. This is called the 0th element, and this one is called the first element. Since it is a 2 qubit state, single qubit state, in single qubit state you will have 2 states, and those 2 states are like this. And for the other state is ket 1. This will be in the form of 0 1. Okay. Suppose, and these two things can accommodate only values of only one, either one or only two things. Suppose if you want, and this forms where your circuit for single qubit will be like this. Only one row, one wire. And if you want to if you perform X gate, NOT gate means, and this one is in the 1 0, this will be converted into the 0 1. Now suppose if I want to have 2 qubit system is, you need to perform tensor product between 2 single qubit system. That means tensor product is symbol is like this, and if you perform this one, and this is simple, take the first element and multiply with this vector, that means it will be like this, 1 of 1 0, 0 of 1 0, and if you see how much 4 states will become, 4 states you will come. Then this one, this is the 0th element, this is the first, this is the second, and this is the third. And if you convert these index places in the form of zeros and ones means, you will get these values. Those are index values. That means 0th place, first place, second place, third place. If you want to build a 3 qubit system means, again you need to perform like this. So in total you will get 8. Now index positions will keeps on increasing. It will be a 3 position. Now this one will be 0 0 0. This one is 0 0 1. This one is 0 1 0. This is 1 1 0 0. And so sorry, 1 0 1. And this one is 1 1 1. Like this it will keep on. As the qubit system increases, similarly you can generate the gates for this one. Suppose if I want for single qubit system, X gate is given by this is the X gate. For 2 qubit system, just do the tensor product. X element wise you can do this. And what you will get? You will get this is the X. Just a simple math. This whole process using tensor product only we can build complex qubit system from simpler qubit system. Any doubt, sir? Shall I go to the next slide? Next slide. This is amplitude encoding. Amplitude encoding means here what we will do, suppose if your data is your state is like this, say comma 3 comma 4. For basis encoding what you will do, you will convert this 3 into what? 0 1 1. Sorry, 0 1. For 4 1 0 1 0 0. Okay, this we can do this, and the states will be like this. From here 3 qubits are there, here 3 qubits are 4. If 4 means 4 plus 4, 8 qubits will be you need. But amplitude encoding, what you will do is you just do the normalization for this one. That means suppose if my vector is 3 plus 4j, what is the normalization of this one? 3 by 5i plus 4 by j, 4 by 5j, right? And this one will be the components, will act as the components. That means 3 by 5 of 3 qubits means it is in the first state means like this. And what about this one? 4 by 5. Second component is 0 0 1. This one is called the amplitude. First do the normalization. Madam? 5 normalization. You will do just for take the norm of this vector. Norm of the vector is root of a square plus b square. And divide this one. Root of a square plus b square means 3 square plus 4 square equal to 5. And if you divide by this means you will get this one. And this one is there, no, this multiplier, that is called the amplitude. And this I and j's are called the basis, computational basis. Okay. Now here how will you do this one? This is nothing but a trigonometry, right? You can think it of as a trigonometry. I mean sines and cosines. So here the trigonometry means it's just a rotation. You can apply the rotational gates to get this amplitude encoding. And what are these? Here I have shown U stands for unitary gate. Here I have given for example I have taken this rotational y axis, y gate, about how much degrees or how much radians, some radians. It depends upon your initial values. And there is in Qiskit there is one function called initialize function which will take care of your data values. Initialize method. This is how you can use Rx gate and Ry gate. It is one using this. If you use these two gates, means this state preparation is called Motanen state preparation. And this is the representation of this 1.767 is then Ry of that arbitrarily it has been applied. It is not mandatory for every amplitude encoding you need to give this value. That initialize function or method will take care of this one. See how this 100 is converted into this form. And angle encoding. Actually, the main disadvantage of previous one, that means basis encoding and amplitude encoding, is because as the value of this features, as the number of features increases, your qubit requirement keeps on increasing. That means it is both number of features and qubit requirements are proportional to each other. And as the number of qubits increases, your gate complexity will increase, and those gates will induce, generally multi-qubit gates will induce errors or noises. And again, this noise is separate research part. So your calculations will not be up to the expected one. But here, this angle encoding will take care of those qubit requirements, as well as it will induce the non-linearity, so that your data encoding data will be somewhat better when compared to the previous two schemes. Here we will induce, instead of using the gates, we will induce the angles for every feature. Again, that will be taken care by initialize. This is the advantages. Here it will use the trigonometric function, so that nonlinear relationships will be captured. Only these two things. And here in quantum machine learning, non-linearity is essential. So we will use this one, angle encoding, in QML. Now this is the graphical representation. If you take what is the state of this one, means initial state will be like this. Since 4 qubits are there. And what about the gate composition? Gate, it will be if you perform this matrix, means it will be 2 to the power of 4 by 2 to the power of 4. That means 16 by 16 matrix will be there. Now the second part is the answers. This is very important. Here is the actual computations or processing your quantum state will happen. And generally we will use the parametric quantum circuit, PQCs. That means parameters, just like in gradient descent, what we will send the theta values, here also we will send some theta values or parameter values to the quantum computer from classical computer. Okay, now the structure of answers and initial parameters can have significant impact. That means your encoding, data encoding as well as the number of qubits will have huge impact on the processing accuracy of your algorithm. And these are different types of answers. I will share you these details. This is mean field and hardware efficient things are very important. Here what I had done this is the circuit process, and the second function, this is the I am creating the cost Hamiltonian operator, and here the third one, optimized circuit. This is the place where optimization will happen, and last one is whether that given input is sorted or not, it is checking. Okay. Now if I run, actually I had tried to create the random number list of random numbers by using the random module between 1000 to 1 lakh, but I got an error because of this memory issue. So I changed my input data to this one, simple input data, which is between 0 and 100, and let me run this one. This is how, see how many passes it is taking. This is our final sorted data set. Oh. That is our sorted data. This is simple. I will share the code also, madam. No need to worry. But the thing is, you have to install few installations are there, and I will show one more machine learning algorithm. This is about this generally used in the finance, just like stock market. How can we optimize your portfolio? Here I have taken few 10 companies, and what I had done is, this is the Y Finance is the module that is being created by Qiskit Python, only Python. And this Y Finance is a module that is being developed and maintained by Qiskit ecosystem. So I have downloaded that one, and remaining things as usual. Here what I have done, first tickers for the, in stock market there will be for every stock, they will give some abbreviation. Those we call it as tickers. And for APPL is the Apple and MSFT is Microsoft, like that. And I have created one asset name where I have included the stocks name of the companies along with the which domain they are in, whether it is a tech or energy or some retail or those things. Then I have taken the time period. Here I have taken the time period of almost 2 years. This is the one. Then this is just like for printing purpose, for visualization purpose. Here is the raw data. This is some preliminaries I have done. And this is the place where covariance matrix. I think how many of you know about covariance matrix? In PCA, you will get it. Covariance matrix. So that I have included. PCA is very, very important. And it is, this is the place where actual optimization is occurring. These are all, actually here I have included those Hamiltonian operators as well as the unitary operators. Only quantum will go with the Hamiltonian operators and unitary operators. It depends. And this is, let me run all these things and we'll switch. Let me run this one. See, this is the one. Here I am getting some data. What is this one? Single position is out of bound. Okay, I will rectify that one. This is the again you are getting the error. Somewhere I have index 0 is out of range. I will convert this. I will after modifying I will send it. Sir, actually quantum is nowadays except Microsoft's Q Sharp. Remaining all are employing this Python only. And IBM is slowly shifting from Python to Rust, RUST, because Rust is even have performance wise it is superior when compared to, at circuit level it is superior when compared to Python. Python is needed, sir. Python is needed. Anyhow, there will be some, there are APIs is there. You can directly, if you learn that APIs means even you can write in one, you can write this in one language, that directly you can, using APIs you can convert into this one. And one more thing, if you are using, suppose if Pennyline is the one which is used for quantum algorithm, sorry, QML for machine learning, those using that framework, you can develop your QML programs using Pennyline. IBM has provided some APIs, so that using that APIs you can run this program, Pennyline programs, using that APIs, and you can run directly in the quantum hardware, IBM quantum hardware. Pennyline is Pennyline communication purpose, general Qiskit only. So this small change is there. I will change it and I will share to sir. So there is lot to say. Okay. If you have any doubts, please ask me. Otherwise, you can contact me also. There is nothing. Huh? I will share this code. I am totally. I am having 6 codes. I will share this to sir. He will circulate it. Okay. Okay. Thank you. Thank you. Take it.
Thank you, sir, for sharing your invaluable insights and deep expertise with us. The session has truly strengthened our understanding of quantum technologies and inspired every learner here. We'll have a break for 15 minutes right now, and it is under speech already waiting. So please attend that session to everyone. A hands-on exploration of quantum computing and circuits. This session is delivered by Mr. Arya Mishra, sir, research engineer at IBM Quantum, specializes in building real-world quantum applications. We warmly welcome you, sir.
Thank you. Hello, hello. Hello. I'm audible. Okay. Hello. Yeah. Thank you everyone for inviting me. And in this session, like, this is my first full-length workshop session, so I'll try to like keep it uh, as interactive as possible. So feel free to interrupt me at any point. I would prefer if it's like not like long monologue of whatever I'm saying or speaking of. So feel free to interrupt me at any time in this session. I'll keep it quick and simple, and I'll like start off from the very basics of like linear algebra and how the Heisenberg picture came into play, and how that like led to quantum computing, and how like at the end of it all, you can build your own quantum circuits, do your own quantum research by using Qiskit. So yeah, starting off. Uh, Let's start with why we use linear algebra for quantum computing. So Werner Heisenberg came up states quantum particles. So yeah, this is basically a definition. The reason Hilbert space is used because of superposition as well. So now what does superposition mean? Superposition is that if like the very famous Schrodinger's cat that thank you. So I think everyone is aware of what Schrodinger's experiment was. So basically, it's a thought experiment that says that a cat can be alive and dead at the same time, simultaneously. So what that means is that, let's say we have got, I'll explain what this rotation is soon in the upcoming slides, but let's just consider this to be a vector, right? Now this vector, let's say this has an, let's say this has a coefficient called C1 and this has a coefficient called C2, then what this means is that this quantum state can be written as a sum of these two, and with two coefficients C1 and C2. That is basically what superposition is saying in the mathematical interpretation. So that's about it. It's just a sum of two vectors. And then next thing is complex amplitudes. So C1 and C2, just like I mentioned, can be complex in nature. Why? Because again, the very famous Schrodinger equation is I h cross dou psi by dou t is equal to h times psi. Again, psi is just a notation. Just think of this to be a vector. And over here, it is basically a quantum state. So once you solve this equation, you arrive at like now h. If we like kind of break down h further, we know that h is nothing but in the classical space, h could be thought of as energy, right? The energy of a system. So like this could be written as kinetic energy plus potential energy in the classical space, and that in the quantum space might be written as uh, considering all the constants to be equivalent to 1, kinetic energy would be a square of the square of a gradient plus potential energy would be some v dependent on position x, right? Now from this we can see that this is basically breaking down into a wave equation itself. So this will become dou 2 psi by dou x square plus v of x. Now we've got a dependent energy, dependent variable over here on x, and then we've got a double differential over here, and we've got a singular differential over here. This times psi, of course. So when we solve for psi, we realize that from this it could be seen that it's a wave equation, and we realize that there is a phase coefficient that comes into play over here, and since there is phases, it like basically means that complex vectors or complex coefficients are required to represent our represent any quantum state. So that's why we have got, and that's why in the Hilbert space we use complex amplitudes. Finally, projection and measurement. There's this thing called Bonn's rule. Now, what Bonn's rule states is that, now again, since it's been established that this is nothing but a wave equation, when we think of probabilities in quantum computing or in quantum mechanics, we see probabilities to be the intensity of a particular wave. Now, since it is intensity that we're calculating, it is nothing but amplitude squared, and that is what probability is in the quantum domain. So when we look at, for example, we have got, let's say psi is equal to a times x. X can be any vector over here again, plus b times y. Now x and y form an orthogonal basis. So like similar to the classical Cartesian space, x can be, let's say, I cap, y can be, let's say, j cap, right? It is the same fundamental over here as well, and these form a complete orthogonal basis. Let's say we are looking maybe in the 2D domain in this particular case, but otherwise, even if we like do 3D, then we'll just add an extra orthonormal basis vector where all three of these are perpendicular. Now, if you were to calculate the probability of this state psi, so the thing with, like I mentioned, with superposition, what happens is the cat can be live and dead at the same time. It is just the state that we measure it in is what is known to us. Now, we can't know the complete state that this has over here. Whenever we do measure what this is, we would either get x or y or z. And why is that? Because again, like uh, it's probabilistic in nature whenever we do measure a quantum state, and these probabilities are defined by these coefficients over here. So if I were to find the probability of this state collapsing into X on measurement, then that probability would be equivalent to this. Now, when I write this over here, again, this is again Dirac notation, and it's of course not intuitive by the looks of it right now. So this can be seen as a dot product. So when we do this operation, what's this breaking down into? We have got X psi is equal to A let me know if it's visible. Is this? Oh, it's fine. Okay. Just write this better, right? Plus C. So again, this in this particular instance, since x, y, z I had mentioned were orthogonal basis vectors, and could also be thought of for the ease of visualization and understanding as I cap, j cap, k cap. This is going to be equivalent to 1. This will become 0, and this will also become 0, because it's nothing but I cap dot j cap, and this is nothing but I cap dot k cap, which is, of course, since it's orthonormal in nature, the cos 90 part of it will become 0. That is the same logic, but over here I've written the same exact thing in Dirac notation, the same thing that applies in the classical space over here. And from this we can see that this would become A, and the square of A. Now since A is complex, we take the modulus of it, and since probabilities can of course not be complex in nature, neither can they be complex nor can they be negative. So what we do is we take the modulus of this and then we square it in order to get the probability of the measurement of this being equivalent to X. So the probability that we see X is equivalent to A square. Similarly, by similar logic, if we operate Y on this, when we operate Y on this, we'll get B square, and when we operate Z on this, we'll get C square. So that is basically what the Bond's rule is saying, and this comes from the concept of intensity in waves, where amplitude square is equivalent to the intensity of a particular wave, and that was kind of utilized to figure out the probabilities in quantum mechanics, and based on that fundamental is where this rule had come from. So that's exactly what it states over here. If an observable X is measured, the state vector psi of a quantum system collapses to some X, and the collapse has a probability of this, which is nothing but amplitude square of that particular X component in the wave function that we had. So this psi over here is also called the wave function. So whenever I refer to wave function, it basically just means the overall quantum state of a particular system that we have created or have under consideration. So yeah, this is basically just a Dirac notation. Now, again, now the thing is that these are unlike I cap, j cap, k cap, which are basically just like orthogonal notations that we have got for like 3 different axes in the Cartesian space. Over here, we do not really have a real 3D space or a real 4D space where we are kind of like representing quantum mechanics. This can be an n-dimensional space. And now when we are dealing with this n-dimensional space over here, for the ease of interpretation, this psi can be treated as nothing but a simple matrix. So whenever we look at Dirac notation, then psi like this is a column vector, and this is known as the ket notation, ket psi. So this is ket, and this over here is known as the bra notation. So when that comes together, this over here, this is known as bra, this is known as ket, and this is also called as the bracket notation of quantum mechanics. And now anything in the Heisenberg picture is represented by the bracket notation. Now whenever we see this, then we should know that it is nothing but matrices. So like whenever there is any quantum information problem that we are faced with, then it could all be interpreted as a superposition of matrices. So let's say we've got a state vector psi over here. Now let this be let's say 4-dimensional state vector. So the bra of psi, sorry, the ket of psi would look like this: C1, C2, C3, C4. Is there a duster I can use? The ket notation of psi could be represented like this, where C1, C2, and C3 are complex in nature. Now, this is a 3-dimensional state vector that I've taken. Again, since 3-dimensional is easier to draw analogs with classical Cartesian coordinates. So just for the ease of understanding that I've taken this 3-dimensional vector over here, state vector. Now, when we convert this into the bra form, then, so since this is a, like this is a column vector, this basically becomes our row vector, as is mentioned over here. But there's another catch to it. Now, once this conversion has happened, since these are complex in nature, this would also be the complex conjugate of what C1, C2, C3 were. Now, why is this done? Because the Hilbert space is also known as an inner product space. Now, what does this mean? It means that in this space, this concept of inner products exists, and this is what an inner product is. To put it in simple words, again, to compare it to the classical analog, the inner product is very similar to a dot product between two vectors. So if we had two vectors v1, v2, then v1 dot v2 is logically equivalent to v1 inner product with v2. So what this means is, now since we, let's say if we've got psi, this very vector that I have defined over here, if we take psi's inner product with itself, then we'll have C1, I'll just write it all down, C1 star, star, C1, C2, C3. So when we do this matrix operation, this multiplication between the two, we can see that this will become nothing but C1 square plus C2 square plus C3 square, the modulus of all of these. So again, now when we look at, let's say, if we had two Cartesian vectors, let's say we had A1 I cap plus A2 j cap plus A3 k cap as V1, and similarly as for V2 we had A2, let's say B1, B2 and B3. I think a better notation would be A1, B1, C1 and A2, B2, C2, I cap, J cap. So now let's say this is V1. Now if I took V1 dot V1, then that would give me A1 square plus A2 square plus A3 square. So as you can see, the dot product with itself over here was a square of amplitudes, and that's the exact same logic as, let's say, if I had two Cartesian vectors in 3 dimensions, and if I took a dot product between the same vector, which is the square of amplitudes in this case as well. So in that sense, it is logically the same thing. The inner product is nothing but logically equivalent to the dot product of anything in the real in the classical space. And yeah, so that's basically what this says. The inner product gives the amplitude, and this over here is an operator. Now, how does that make sense? How is this an operator over here? Now, we know that the psi that we had defined in ket notation looks like this. So normally when we look at it like this over here, from the look of it, like if we think classically, if we think from the classical perspective, this matrix multiplication should be invalid, right? But when we are doing this over here, this is not a matrix multiplication. This is more of a tensor product between these two. Now, what is a tensor product? A tensor product is nothing but we take this element first and we multiply it with all of these. Then we take this element, multiply it with the same thing, and then we take this element and multiply it with the same thing. So what happens is the size of the resultant matrix. Now, this matrix is 3 cross 1, and this matrix is 1 cross 3. When we take a product like this, our resultant matrix becomes 3 cross 3 because our it becomes C1, C1 star, C1, C2 star, C1, C3 star, C2, C1 star, 2 square. So basically, our dimensions have have dilated, and now we've got a bigger matrix after having done this. Now, over here, our resultant, as you can see, was a real number, the sum of square of amplitudes. But over here, our resultant leads to a matrix. Now, since again we have got a matrix over here, we can operate this once again on any other state vector. Did this. Now, what we have done over here was the outer product between psi and psi, right? So psi we knew was 3 cross 1, but once we did this, it became a 3 cross 3 matrix. Now, since it became a bigger matrix, this could operate on more 3 cross 1 matrices. Now, that's what makes this, since this has the ability to like operate on another state vector, what this becomes is an operator. But the operator we constructed over here is a special case. Why? Because we took two state vectors and both of these state vectors were the same, which was our wave function basically. So this outer product between the wave function is what led us to creating a density matrix. Now this density matrix is represented as rho. Rho is a notation that's used for this. And if I were to write a formula for like representing any density matrix, then it would be equivalent to the summation of pi phi I outer product phi I. Now this is considering psi, which is our wave function, is the summation of ci phi I, where phi I are our basis vectors and psi is our, of course, final wave function. So if we were to represent any density matrix, that will be equivalent to this, where pi is nothing but probability. Now probability, as as I had mentioned previously, is nothing but amplitude come modulus whole square. So this is how a density matrix is constructed, and that is how we have arrived at this point. Now another interesting thing that you would see over here is that the trace is nothing but C1 square plus C2 square plus C3 square, which is the sum of probabilities P1 plus P2 plus P3. And since our wave function, since I had mentioned that it's a three-dimensional wave function, and uh, yeah, since our wave function is wholly represented in these three dimensions, the sum of all of these probabilities will be equivalent to 1. So the trace of our density matrix for a pure state in specific is going to be equivalent to 1 in this case. And yeah, the density matrix rho described mixed states and the expectation value of A is equal to trace of rho A. So what this means is expectation values once again. If we had an operator, again, an operator is, let's say in our case, since we're dealing with 3 dimensions, is some 3 cross 3 matrix that can operate on a 3 cross 1 state vector, right? So whenever we take an expectation value of any operator, then that is measured by this operator acting on our state. So this operator, once this 3 cross 3 is being multiplied by 3 cross 1, that can of course be denoted by O times O times get of psi is nothing but the operation of this matrix on this matrix. It's a simple matrix multiplication. Now after this is done, our final resultant matrix would be another 3 cross 1 matrix, right? So now our bra of psi is a 1 cross 3 matrix. So once we take the inner product between this and our resultant O cap psi, then we'll have once again a real number, which would be the output of this expectation value psi O cap psi. Now this operator, usually whenever we talk about operators in quantum mechanics, when we look at, let's say in the classical space, there's quantities like momentum, position, let's say kinetic energy, let's say potential energy, any of these properties, any of these measurements, how they are done in the quantum space is by using these things called operators. So an operator is nothing but you could say a physical measurement of a certain quantum state that we have under question. Now the expectation value of this operator once again is nothing but a form of, let's say, it is in essence basically a probability of our state having a particular uh, let's say a particular position, a particular position, a particular momentum, a particular kinetic energy, or a particular potential energy. So that is what is happening over here, because as we had seen previously, that doing psi for any basis vector, let's say phi and psi, is going to, the square of this is going to give us the probability of that particular it will give us the probability of our wave function collapsing into this particular state over here, if our wave function comprises of this state. Similarly, when we do this, then we've got an amplitude of that particular observable that we observed on our wave function, and if we square this, that'll be nothing but the probability of that particular state having had uh, this momentum or this observable that has been acted on top of it. So that is in essence covering Dirac notation and also things like operators and density matrices. So moving on. Or if anyone has any questions, then you could feel free to interrupt me at any point. So if there's any questions, then yeah. Seeing none, I'll move on. So now let's move from quantum mechanics to quantum computing, and like the basically our transition from not just classical to quantum, but our transition from classical bits to quantum bits, or also known as, also abbreviated, or also said in short as qubits. So a classical bit may be, let's say, defined like this, where each of these are registers, right? So each register can have one of two values. It can either be 0 or it can be 1. So if, let's say, I've got a total of n registers, So each of these positions can occupy either 0 or 1. So that'll be 2 times 2 times 2. So the amount of information I can store at the end of it is 2 to the power n, right? But qubits change this, right? Now the thing with qubits is that each bit, let's represent a set of qubits as q0, q1, q2, q3. Classical register could have either 0 or 1 value, but now the same thing in the quantum paradigm, in quantum computing. Imagine these to be quantum bits or like quantum registers. Now each of these quantum registers could store actually a superposition state, which is each of these could be Q0, for instance, could be A1 times 0 plus A2 times 1. Now what are 0 and 1 over here? Now if we look at it from a very basic, very fundamental perspective, then 0 and 1 could represent the ground state and the excited state of a particular electron. And if you were to represent these in terms of bits, so we kind of just capture that information of any electron being in the ground state or any electron being in the excited state, and we can mathematically represent that as 0 looks like this matrix over here, and 1 looks like this. Which one?
1001. Written 1010.
Okay, yeah, my bad. Yeah, thank you for the correction. So yeah. So 0 looks like this and 1 looks like this, and these become the building blocks of any of the quantum bits, or any set of quantum bits that we talk about when it comes to quantum computing. So basically Q0 could take this form, Q1 could also take a similar form, maybe with coefficients 8, B1 and B2. Similarly with Q3, Q4, etc. So what this means is that each of these qubits, they do not belong in the set 0 or 1 anymore, but rather they lie on a sphere. So it could take any value on this specific sphere known as the Bloch sphere. So any quantum bit could be represented as a superposition, and the superposition can take any value in this sphere over here. And now the question arises, now the thing is, why a sphere? Because usually whenever we represent any of these quantum states or any of the wave functions, then they're usually normalized in nature. So the sum of squares of these coefficients should be equivalent to 1. Why? Because how we had discussed some time back, that all of these coefficients are nothing but, once they're squared up, they should sum up to a probability. So because of that very reason, this is a condition that is being fulfilled here. Now this is nothing but the equation of, this is otherwise the equation of a circle, but we cannot represent like quantum states on a circle because it's highly restrictive in nature. Why? Because we have only got one parameter theta, which would influence like any of our states. And again, tracing back, the Hilbert space is complex in nature, and quantum states are waves. So because of that, we also need to have another component known as the phase. Now, with the introduction of this phase component, any particular with the introduction of this phase component, any particular quantum state lies on a sphere. Is yeah. So that's basically what this says. There is superposition and there is phase, and the richer state space over here is nothing but a sphere, and the geometric view of this would be on the next slide over here. Yeah. So this is what is known as the Bloch sphere, and as you can see on the geometrically opposite ends of the, on the longitudinal ends, yeah, on the poles there is, yeah, that's the right word, thank you. So on the poles there is our 0 state and our 1 state, and there is a, yeah, and this is along the z-axis. This is our like standard representation of what a Bloch sphere is and how it is interpreted most commonly in quantum computing. So these lie about the z-axis, and any particular quantum state on this sphere is represented in this form over here. And now the question arises that why do we use theta by 2 for this representation? This is nothing but this is basically for example, if you got this vector over here, this particular quantum state, then it is nothing but the projector of this on the x-axis, on the projector of this on the projectors of this basically kind of add a cos theta by 2 component to 0 and a sin theta by 2 component to the one state, and the phi over here is nothing but the phase between them, and this is what a single qubit pure state might be represented in on the like using these projectors. So any quantum state might have this representation over here, and as you can see, the sum of the modulus of each of these coefficients would sum up to 1. So yeah, and this is like the theta by 2 over here comes because the representation over here is in the SU2 form. So this is the SU2 notation. And now once we start discussing polys, and the polys are basically nothing but the projections of each of these onto the x, y, and z components of the block sphere. The expectation value of each of the polys. We'll go into that later. But once we start taking the expectation values of polys, it'll become more clear as to how it'll help us trace back to the projectors of a regular sphere, which like as all of us might be aware of, the x component should be cos theta sin phi, and cos theta cos phi, and similarly sin theta of each of these x, y, and z components. So that is something that will become intuitively clear once we start taking the x, y, and z projections of this onto a sphere. So the spherical coordinates could be traced back by taking these projections. Yeah, so for a state rho, now again, when we represent any state as a density matrix, then this is nothing but equivalent to, let's say, our rho, just tracing back to what we had discussed some time back. Rho is the outer product of our quantum state, of our wave function. Then basically, yeah, this psi times x psi, which is the expectation value of x, is nothing but equivalent to the trace of rho times x. Now this is something that could be derived, but again it is a pretty lengthy derivation. I would not go into that right now, but this could be done as an exercise by you whenever you want. It's not a very difficult derivation. It's just just lot of solving which would take some time. But anyway, this is so basically for any state, basically what I discussed, the x projection is nothing but the expectation value of x, y projection is nothing but the expectation value of y, and z is z, and these are nothing but the coordinates on the sphere of any particular quantum state. And moving on, any block vector might be represented like this, where these are again coordinates on the sphere, and the pure states have the radius of the sphere equivalent to 1. So any pure state would lie on the exact exterior of the sphere with a radius of 1. However, any mixed state would have a radius that is less than 1 and would lie somewhere internal to this block sphere. And yeah, this is also another exercise, which is measure Pauli operators to reconstruct R. This is something that, yeah, so these are the Pauli matrices that I was referring to on the previous slide. So the Pauli X matrix is nothing but a bit flip matrix. Now, why do I say that? Because let's say we have got the 0 state, which is represented like this. If we operate the X Pauli X matrix on top of this, then this is going to give us, so this is nothing but equivalent to 1. So the X matrix causes a bit flip. Similarly, if I were to operate Z on top of on 0, then again this times this over here would give us nothing but the 0 state back, but and this would basically just be cancelled out and become 0. But if I were to operate this on 1, as you can see, there will be a phase flip. Now, how does this make sense? That is because the basis of the, like when we do decompose this poly Z matrix, then we get a set of like eigenvalues and eigenvectors. And what we observe interestingly is that the eigenvalues of this are going to be nothing but equivalent to 0, 0 and 1. And this will have an eigenvalue of +1, and this will have an eigenvalue of -1. So yeah, basically if you were to like represent this in the outer product space again, that'll be equivalent to 0 outer product with itself minus 1 outer product with itself. How? If I were to break this down further, then 0's outer product with itself is nothing but this over here, which is going to be equivalent to 1 0 0 0, and 1's is 0 1 0 1, which is equal to 0 0 0 1. Now when we do subtract these two, we will get our poly Z matrix. Now, of course, calculating the eigenvalues and eigenvectors is something that it's something that I would not be doing right now, but it is pretty easy. You could solve it by yourself, and yeah. So the eigenvalues and the eigenvalues of this are 0 and 1. Similarly, the eigenvalues of x give us something very interesting. So the eigenvalues of x give us superposition states. Similarly with y, which is a superposition between 0 and 1, and they are represented as plus and minus. So these are the eigenvectors of the poly x gate. Now how are they represented? 1 by root 2 cause normalization between two terms. These two are also pretty. These two are also important states, because the thing is, like especially in the context of error correction and like the very basics of error correction, because this helps combat phase flip errors, and the poly X gate over here is also known as the phase flip operator, because if this is no, this is a bit flip operator, this is known as the phase flip over here. But once this poly X is operated on either of these, then this is going to give us a minus of minus output, and this is going to give us a plus output itself. Why? Because the eigenvalue of this is -1 and the eigenvalue of this is +1, and yeah, so these are two other commonly used states in quantum computing, the plus and the minus state. Similarly, once we calculate the eigenvalues of this, it gives us 1 by root 2, 0 plus the complex coefficient, yeah, the plus the phase j times 1, and 1 by root 2, 0 minus phase j 1. So this is nothing but this is adding an extra phase of I on the superposition of 0 and 1. So in order to introduce, yeah, so even these states are again uh, like the decomposition of the poly y, and again these also can be calculated as an exercise. So yeah, so basically this is nothing but you would get eigenvalues of 1 and j, and this will be j and 1. So these would be the eigenvalues that you will arrive at after solving this. Now again, the question that might arise is that isn't it supposed to be 1 and minus j? Because that's what this kind of summates to. But there is this concept of taking the global phase out from this, and then like once you take the j out of this, once you take j common between these two, then this will become j and this will become 1, and j can be cancelled out because that's the global phase. So global phases are usually cancelled out in quantum mechanics because they hold no meaning at the end of it, at the end of our calculations. They add nothing to the probability of any of the states or the probability of measuring any state to be at any point. So usually whenever there is a global phase of e to the power I phi in our equation, then that could be taken out. So psi is going to be nothing but equivalent to e to the power I phi into psi is, yeah. So these are the poly I, poly x, poly y and poly z operators. And if I were to find the x coordinate, then again the expectation value of x is going to give us the x coordinate, y the expectation value of y would, and z the expectation value of z. And now the expectation value could be basically cos theta by 2 0 plus e to the power I phi sine theta by 2 1. This is a general wave function as I had mentioned in the previous slide. So if you take the expectation value of x, y and z with this, then it will give us nothing but the coordinates on the block sphere uh, uh, for any of the, for this wave function, the projectors on the block sphere. So I could in fact solve one of these to make it more clear. Um, and like through solving all these, it'll become much clearer on why there's a theta by 2 that we're using and why we're using the SU2 notation for representing any quantum state on the block sphere. Theta by 2. Now this is our general wave function as I had mentioned. Now if I were to take psi x psi for this, which is nothing but the expectation value of x, what we arrive at is going to be uh, e to the power I phi sine theta by 2 and cos theta by 2 minus I phi sine theta by 2. So this matrix multiplication is what we'll arrive at, and I think that's correct. So after we do this, we come at e to the power I phi cos theta by 2 sine theta by 2 plus, yeah, e to the power I phi minus I phi sine theta by 2 cos theta by 2. Yeah, I think that's correct. Yeah, looks fine. So if you were to like multiply and divide by 2 over here, then we'll get 1 by 2 times e to the power I phi sine theta plus e to the power minus I phi sine theta. Sine theta taken outside will be 1 by 2 sine theta, and this after we expand would be equivalent to cos theta plus I sine theta plus cos theta minus I sine theta. This is going to be equivalent to sine theta cos theta. This is nothing but the x. Sorry, this will become phi. My bad. Sin theta cos phi. All of these were phi terms, but that's nothing but the x component on the sphere, the general x component. So arriving at this, we end up arriving at the x coordinate or the x projection of any particular vector on a sphere. And the same thing can be done with y and z as well. And yeah, finally we would realize that this looks like basically we'll just decompose into the x, y, and z components on of any particular vector on a sphere. Now moving on to operators. There's two major types of operators that we deal with in like quantum computing. One is the Hermitian type, the other is unitary. And Hermitian operators are nothing but observables. As I mentioned, observables are nothing but like measurements, physical properties of let's say any particular quantum state. Now these are characterized by this A dagger equals A. Now dagger is nothing but the conjugate transpose of like this matrix A. So what this means is this is A transpose with the conjugate. So basically, it's a transpose of A and the conjugate of all the complex elements that reside in the A matrix. And what this means is that there is real eigenvalues. Where are the real eigenvalues? Because any physical property that we measure at any point has to be, of course, a real number because that's something that we're measuring. It's a measurement and it cannot be complex in nature because that'll make no sense. So that's why a Hermitian operator, uh, observables are Hermitian operators with real eigenvalues, and yes, and basically projectors from eigenstates are Hermitian in nature. So this. So basically, this should be Hermitian in nature because again, even this translates to an operator. And moving on to unitaries, unitaries are nothing but, so unitaries are not measurement. I mean, they're not measurements, so they're not like an observation that you're doing in a state, but rather they're an evolution of a state. So basically, unitary may be represented in this form over here, IHT, that should add to one with a conserved probability, and that's the reason why. That's the reason why like yeah, it must preserve norm, and yeah, and it's also represented like this because once you do u dagger u in this case, then that should be equivalent to e to the power minus I h t into e to the power I h t. Now, like the dagger of this would basically lead to the dagger of this one observable that is in the coefficient of this unitary operator. Now, in order for this to be equivalent to 1, which is the expected behavior, H transpose should be equivalent to, sorry, H dagger should be equivalent to H. So that's why this operator should always be Hermitian in nature whenever we are defining a unitary, like whenever we are defining a unitary in that form. Now moving on, these are some common single qubit gates. This is the X rotation, Y rotation, Z rotation, and this is the Hadamard gate. Now the Hadamard gate is very commonly used because it creates a superposition of states. And for example, if this is faced with 0, then this will create a plus state, 0 plus 1. And if this is operated on a 1 state, then that'll be 0 minus 1. So that is why whenever there's inputs of 0 into a quantum circuit, once a Hadamard gate is operated, it gives us both the states with an equivalent probability, 0 plus 1, 1 by root 2. For this very reason, the Hadamard gate is important because it is able to create a superposition state from a ground state, from a 0 state. Yeah. Moving on, multi-qubit states are represented as a tensor product uh, between two different wave functions or two different qubits, uh, two wave functions of two different qubits, and they can be written like this. So yeah, that's basically let's say whenever we got like 0 0, it is nothing but, or 0 0 1, or like etc. whatever, like whatever comes beyond that, it is nothing but the tensor product of 1 0 vector with another 0, sorry, with another 0 vector with another 1 vector. So this over here is going to lead to 1 0 0 0. So this will become, of course, since these are two qubits, and since a single qubit has a is a 2 by 1 matrix, this should this should be equivalent to a 4 by 1 matrix, and this is how it's represented. Like basically, what we are doing here is nothing but 1 times 1 0 into 0 times 1 0, which is going to give us 1 0 0 0. And the same thing can be done with 1. And whenever there's multiple qubits, this just keeps expanding downwards with how many ever qubits have been added to the. And so that's basically what it says. Dimension multiplies n qubits, which leads to the power n dimensions for n qubits. So again, in classical bits, we only had 2 to the power n amount of information. But over here, we're creating a vector with 2 to the power n dimensions, which can take any complex value. So that is why quantum bits can store much more information than classical bits. And moving on to 2 qubit gates. Now I'll just talk about one gate in this case, which is a C0 gate, because it's a pretty important gate in quantum computing. Now the reason why C0 is important, as we had seen last time, Hadamard is a gate that generates superposition, and C0 gates on the other hand, this is used to create entanglement. And superposition and entanglement are the two driving factors or driving concepts between in quantum mechanics, and something that also leads to tractable advantage in quantum computing, which could be seen. So basically, this bit influences whether or not this bit is flipped in a C0 gate. So if this is 0 and if this is 0, both of these are 0, then our output over here for this would again be 0 and 0. But if this were 1, then this will lead to a flip. So this will flip and this will become 1. So yeah, if it's 0 0, the output will be 0 0, and if the input is 1 0, then the output will be 1 1. So that's basically what the C0 gate is doing. Yeah, and now moving on to projectors and measurement. So again, this is basically the Bond rule itself, and yeah, that's just been revisited over here. Oh yeah, now moving on to the practical part of the workshop. I'll keep this quick because I know there's lunch break soon after this. There's just like a couple of examples. Hmm? Yeah, yeah, sure. It's just building basic quantum circuits and Bell states. So the creation of Bell states. I'll show one Bell state, and then the rest will be a exercise. Yeah, all right. Yeah, yeah, sure. It's pretty late already. Yeah. I think I'll cover the rest post lunch maybe. Yeah, yeah. It was pretty late already. Oh, till 1:15. Okay, fine. Yeah, I'll finish it. Okay, so if everyone has Google Colab or uh, any Jupyter notebook would be fine if you got the extension on VS Code. The first step is, of course, since we'll be using Qiskit, the first step is to install Qiskit, which you can do by using pip install Qiskit. Now, there's another thing that we'll be requiring, which is, I think it's, we had tried at the start, but then apparently it's not. Okay. Even this is a external institution, right? So okay, so the first step is to install both of these, pip install Qiskit and Qiskit IBM runtime. Qiskit IBM runtime will be used for simulating our circuits, whatever we build, and yeah, Qiskit is our SDK. So, oh, Google Colab exclamation at the start. Yeah, yeah. It's been some time since I've used uh, Microsoft. Yeah. Yeah. So once Qiskit is installed, I think we don't have to restart the workbook in Colab. No? I'll just proceed. Yeah, I'll restart it. So yes, for our very basic circuit, uh, we can start with from Qiskit import quantum circuit, and for quantum information. So most of what we had discussed in the first half, it was all about. Oh, okay, these two. Yeah, yeah, sure. Yeah, I'll just clear the output. In fact, so after the installation step, uh, quantum circuit can be imported from Qiskit and quantum information. So the thing is, in the first half of the presentation, we had discussed some basic like quantum information concepts itself on what is a wave function, what is a state vector, what is an operator. Okay, yeah, this is better. Okay, so after these imports have been written, yeah, yeah, sure, it's yeah, right now. Mm, okay, yeah, fine. Hmm? No, no, I'm using fake backends. Yeah. The Jupyter notebook, right? Yeah. So okay. This is the QR code for the Collab notebook, for the Jupyter notebook. Oh yeah, bilateral CNC, yes. Matplotlib dash. Yeah, sure. I think it was.
It won't be visible in the screen. Just writing. I don't know if it's visible. I'm just writing it. This is the spelling. This is an additional package which needs to be installed so that. But if you just give print of QC or QC
Yeah,
dot draw
without
without
MPL
anything,
also
it
it
will print.
works.
Like don't give the. So if you just remove this MPL, it might print as such. You just remove this. You also want to go around like maybe. Okay,
Yeah,
you
yeah.
have it back, so now you can
Yeah.
just type it and show it with black and stuff.
Or I'll. Okay. So this could be done. Pip install by latex. Oh yeah, I keep forgetting. It worked without the exclamation too. This one I think worked without
Yeah,
it.
it worked
That's very
without
weird. Yeah, this one wasn't. Hmm. So either this can be installed and then the circuit will draw as it is, or this MPL also can be removed if the installation is something that, yeah, yep. It just,
normal text.
yeah. So it is that MPL is used to make the circuit look prettier, but even without it, QC.draw functions as is expected. So what we have done over here basically is we have imported quantum circuit, then we have imported, so this is not being used right now, but we have imported state vector from Qiskit.quantuminfo. Now the quantum info module of Qiskit is basically used for uh, most of the calculations that I had discussed at the start, which involves density matrices, state vectors, operators, and all of this, expectation values. All that is calculated through the quantum info library, the quantum info module, and NumPy is imported too. Uh, this first step was to create a quantum circuit. The one over here represents the number of qubits. So this is basically a single qubit quantum circuit that we have constructed. Now, if I were to change this and make this a 2-qubit quantum circuit, then basically we have just got 2 wires now, and on one wire there's the first qubit, and the second wire is the second qubit. Then after that we operated the X gate, we added the X gate to the 0th qubit. Now the 0th qubit over here is basically the first qubit, which is labeled as Q0, and this is nothing but adding the X gate, which is also in the matrix form could be seen as the poly matrix. The poly matrix is being operated on the first qubit over here, and yeah, then that's what is being drawn. So now, in order to confirm that, since we had imported state vector previously, now what we can do is we can create a state vector from this circuit that we have. So it is important to note that whenever we start off, whenever we are like building a quantum circuit, the starting states of our qubits are always going to be 0. So everything on the left side, on the leftmost side of our circuit, will be a 0 state, and anything that's operated on top of it would basically manipulate our 0th state into something else. So that is something that we could see in this step over here now. So what we have done is we have used from instruction, and we have passed our quantum circuit inside, which is again a 2-qubit quantum circuit now. And once we printed the state, we could see this state vector over here. Just to write it down more simply, it is going to be equivalent to 0, 1, 0, 0. So what that means is, yeah. So what that basically means is that the X is being operated on the first qubit over here, and the second qubit there is nothing that's happening, so it still remain in the 0 state. Oh, I think in state vector convention, yeah, since there is only one operation that's happening, uh, yeah. So basically, this went from being, yeah, this went from being 1 0 0 0 to 0 1 0 0. Why? Because X has acted on top of that over here. And this over here is nothing but 0 0 if you remember, and this will become nothing but 1 0. So this has been flipped using the X gate, and this has become 1 because due to that reason, and 0 remains 0 in this case. So that is what is happening in the matrix form that we have done through a circuit right here. And this operation, just so it's easier to understand, is X. So we build the circuit and we visualize what is happening, what's the mathematics that's happening behind it. Now, I hope it's clear. Moving on, let's proceed with operators. Now, operators and polys are again something that can be imported from the quantum info library. And a poly may be initialized using this over here, poly Z. This could also be done using, I think it might be somewhere here itself, or if it's not, I'll write it again. Okay, no, it's not. I think this was covered, no? Yeah. So this, instead of having to write this extended, this full thing as, first we have considered the poly over here, then we have converted that into an operator. Another way we can do this is, we can import this thing called sparse. Yep. And our operator would just be mm, so yeah, either you could use from list or you could use, I think, from label. But yeah, with this, I think from list would be. Mm, hmm. String. I think labels and coefficients are separate lists, right? Yeah. Yeah, exactly. It shows the exact, and that keeps going. I don't know. It came for a moment, but then it's
When you turn to type, you can't see it.
yeah. Yeah. Should I use the code suggestion itself? I'll just remove the unnecessary bits. So it's a list of tuples, a tuple with like coefficient and label. Yeah. Uh, now suddenly.
Yeah, there may be root there.
Okay. Oh, okay.
This is your laptop or like your laptop?
It's this.
Yeah, just try it here directly.
I think just one Z1 and we can just remove that. We can just remove the second term. No? Yeah.
This is for the two. This is for two qubits, right? So
No, it's this is an entirely
this it's just an independent one.
yeah.
I think this should work. Just see. Yeah, so
Okay, yeah, it's a 2 qubit thing. I changed. of a sparse operator. Maybe we can just change this to operator. That'll just become easier.
Let's just comment this out.
Yeah.
Yeah, we got we what we want. The problem was somewhere else.
Hmm.
Yeah, it worked.
Yeah. So yeah, basically our polys can also be constructed using this sparse poly operator. Now sparse poly operator comes in handy when we've got multi-qubit states especially. Otherwise, traditionally what used to be done was that first you initialize a poly for z, then you initialize a poly for x, and you convert all of that into a poly list first, and this poly list starts on multiple qubits, which is again a relatively lengthier process when we've got like more than one qubit. For single qubit, the previous method, where which might be in your Jupyter notebooks right now, where basically a poly z is being initialized, is something that might work on a single qubit state vector, but for multiple qubits, uh, I would say a sparse polyop initialization is much more efficient. So basically over here we have got nothing but a tuple, with this is the poly operation that we are doing. This is the coefficient. So even the coefficient can be altered. So if you got multiple terms, this could also be kind of represented as a sum of polys, and like you can add more tuples with other differing uh, poly alpha. In this case, it's just an alphabet, it's just a string, poly strings, along with a certain coefficient, which could also be like 1.5, any float value, and yeah. So that's basically what the sparse poly operator does. Yeah, I'll just show the code. So basically, now the thing is, the class of operator after having initialized that sparse polyop is going to be that of a sparse polyop. And whenever we do this method, what we are doing is we're creating a poly x and we're casting that as an operator type. This over here was a sparse polyop that is being casted as an operator. The tensor between these two, from the definition of a tensor product. Now this would be a 2 by 2 matrix. This over here would be a, I think, a 4 by 4 matrix. Then after having done a tensor product, let's look at what we get. So yeah, the tensor gives us an 8 by 8, 2, 2. So yeah, that's basically an expected output. Oh, yeah, sure. I'll actually just even higher. Yeah. Which one over here? So this changed over here. The operator became a sparse polyop, and before that, you got the output for this, right? This one, this operator over here is being converted to an operator type. So it's operator on operator, and then is it working? It's this. Okay.
And then he became a communication.
Yeah, what's the error? It's showing up. Name operator is not defined. I think, yeah, you should just change the name of this to operator. So that's one another change I made. Yeah, yeah, I think.
Anybody has any questions?
Any questions? No. And so yeah, now this is basically a 2-qubit quantum circuit. This is CX having been operated on that. Uh, now this is similarly when we like take the state vector of this, it'll look like this. This might be on your Jupyter notebooks already, and yeah, and execute. Now another thing is this. There's this thing called evolve. So once we go to state vector, if we use state vector dot evolve and we pass an operator into it, then what happens is, so what? No, never mind. I didn't run the previous cells, but yeah. Anyway, what we're doing with evolve is that if you got a state vector over here, let's say the state vector over here was equivalent to 1, 0, 0, 0. This is nothing but the this state, initial state. When we do an evolve, this is doing nothing but O times psi. So this multiplication is something that evolve does, and yeah, I'll just run through them all. Oh, and this circuit over here is known as this is a Bell state, which is represented as phi plus. It's a very important circuit in terms of quantum communication, and because it is used in QED networks quite a bit. Uh, like all of these Bell states are nothing but uh, like they form in fact the basis, a complete basis for any 2-qubit state, and they're represented like this. Basically, there is phi plus or minus, and there is psi plus or minus. This is basically phi plus, and this is going to break down into, as you can see, these states generate entanglement, and because they generate entanglement, they're of very high importance in quantum communication networks. That being said, the output of this, if you calculate it mathematically, then it'll come out to be this over here. And if you run through your Jupyter notebook, if you run all the cells, then you can see that in action, because estimators are being run on top of this and should give the valid output. And also, whenever you're measuring a quantum circuit, you can add measurement blocks by using dot measure all. So what that does is that basically, if there is no classical resistors initialized already, it initializes two new classical resistors. In this case, two, because it's 2 qubits. So the measurement data of each of these qubits is stored in a classical register, and that is what is being done in this circuit over here. So whenever we run estimator or sampler, which happens in the next step in this notebook, we have to first transpile the circuit, and transpilation is something that I won't go in depth into right now, because that'll be covered later. But transpilation is nothing but the mapping of our qubits or our quantum circuit from from a tree to a directed acyclic graph, which so it's basically nothing but the mapping of our software, uh, of the qubits in our software onto our hardware layer or onto our physical qubits. So that that is done based on that depends on backend to backend. So different quantum hardwares might have different gates that are available to them, or like different qubit connectivity. So based on that, transpilation is an important step, and that's what's happening over here. For a specific backend, this a specific quantum circuit is being transpiled. After transpilation is done, the sampler is run, and the sampler is doing nothing but it's like constantly sending more input states and like constantly measuring data for, let's say, 1,000 times, and then after that it outputs a certain counts, and what counts are doing. So in this case, after you like as you can see, I ran this circuit on a particular backend for 1,000 shots. I got the 00 state 503 times and the 11 state 497 times, which is basically nothing but this bell state over here. So that circuit led to this outcome, and again, like it is not exactly 500 because of because of course quantum backends are prone to decoherence errors and some errors here and there. So it is not exactly accurate, but it is more or less accurate, and it is equivalent to 1 by root 2 0 0 plus 1 1. Now moving on, this is nothing but the initialization of other bell states. Now this is something that you can do by yourself. You know how estimator works, you know how transpilation works from these two blocks. So in the next few steps, what I'm doing is I'm just initializing all of these other bell states. So phi plus is something we just saw right now, phi plus. Phi minus is also initialized at a later step. Psi plus and psi minus are also initialized. And all of these can be run by using the estimator, as had been done in these previous two cells that are shown right above. That's an exercise you can do for yourself. So basically, you can just initialize the backend, you can transpile the circuit, and then you can run your sampler on all of these bell state examples that I have over here. So all you have to do is just run the estimator on top of these, and the sampler on top of these, and then you'll get your output. So this is an exercise that you can do for yourself, and yeah, that being said, that concludes the session. Yeah, thank you. If you have any questions, then feel free to ask at any point.
Thank you, sir, for your informative and balanced presentation. We truly appreciate the clarity and depth you brought to the topic. We would now like to present you with the sampling as total of our festival and as a part of our CoE initiative. We respect we respect our ability to kindly present our total.
Thank you so much.
Thank you, sir. We now break for lunch. Please reassemble by 2 as we continue our journey to quantum.
So I speak in the mic. Okay. Hello everyone. Thank you for the warm welcome. So I know we've just broken from lunch and we're all back, but hopefully you guys can stay awake through this session. So let's just get started. So you were telling me. Okay. Like on screen, okay. Oh, this one, okay. Okay, good. So I move here. If I annotate, will I be able to write on it? Okay, nice. Yeah, yeah, good. Oh, you have a pen. Okay, nice. Okay, so the idea is to give some hands-on expertise, and even before that, I want to give a general introduction to variational quantum algorithms and applications. We will go from a little bit of more simpler, start, and then we will build upon that. So discuss why should we do quantum computing, where should we do quantum computing, when so just think about this, right? If I want to multiply 39 and a number 55, I'm not going to use a supercomputer. I'm going to just do mental math, or I'm going to at the max pull out my calculator, right? So as important as it is to learn quantum computing, it is also important to understand when it makes sense to use a quantum computer. So it's an important question to ask, and it also correlates with what a quantum computer can do that a classical computer cannot. So let us just dive into the talk, and we will go through each of these points one by one. So let's start with, okay, I need to switch it here. So yeah, okay. So let us start with IBM Quantum's mission. So IBM Quantum's mission is to bring useful quantum computing to the world. This is a very short sentence, but it is one that is heavy enough that I can take a whole talk just breaking down this particular, sentence. But let us, for the sake of this session, let us first start by asking, what is quantum computing? So what is quantum computing? I'm not going to go too much into detail because Aryava has already covered quite a bit of like this. So we will just summarize it very neatly so that we can use these points further down the talk. But in classical computing, we are all aware of bits and classical logic circuits, right? So bit is a controllable classical object that is the unit of information. And the math which manipulates these bits is based on Boolean algebra. What do I mean by that? So even before that, let us also learn what is a classical logic circuit. It is the unit of computation in classical computing, and it is basically a set of gate operations that act upon bits and manipulate bits as per your wish, right? And the mathematics that this is based on is Boolean algebra. What do I mean by that? We write a truth table, right? So it's usually a yes or no, true or false type thing that you can refer out of bits and refer out of classical logical circuits manipulating these bits. So similarly, in quantum computing, you have quantum bits which are specifically known as qubits, and quantum circuits and specifically quantum gates which can be used to manipulate these qubits. But quantum bits are slightly more different compared to classical bits, and the reason is that a quantum bit or a qubit, it is a controllable quantum object that is the unit of information, and this obeys the laws of quantum mechanics. It is not the same as classical mechanics which we have in classical computers. So this is a fundamentally different entity. And a quantum circuit is a set of quantum gate operations on these qubits, and that forms the unit of computation here. And the main difference comes in the form of the mathematics. So the mathematics in the case of quantum computing is based on linear algebra, and it is not based on Boolean algebra. So this is a hugely sort of important factor to keep in mind, because where do we see linear algebra? Literally everywhere, right? Especially in problems where you're dealing with a lot of huge matrices, say solving differential equations, or QML tasks where you're updating a lot of parameters and you want to do some classification tasks and the like. So you can see a lot of matrices that are there, that where you can kind of translate the problem into a linear algebra problem that is very compatible with quantum computing. So what else is different in terms of qubits as compared to bits? So a qubit, we've all heard that a bit is either 0 or 1, but a qubit can be somewhere between a 0 and 1. What do we mean by this? So there is a inherent sort of indeterminism in a qubit. So if you want to probe into the state of a qubit to know what state it is in, you cannot know that right away. You need to do something called as a measurement, and this is the act of observation on that indeterministic object that kind of leads to that leads to different outcomes. So in the case of classical classical objects, you take a look at something once, it is, say you take a look at a classical bit, and you observe it as 0. No matter how many times you observe it, it's going to be 0. That's what a classical object will behave like. It is inherently deterministic. But a quantum object, just because you're like, as you do a measurement or an observation every single time, it is not guaranteed that you're going to see the same outcome every single time. It could be 0 most of the times, but it could also be 1. So this inherent indeterminism in some cases is because a qubit can exist in a combination of also 0 and 1, which is what we call as a superposition. A general state in quantum computing, you can represent as, say, a ket 0 plus b ket 1, and this combination it's kind of a superposition, and this in some sense tells us that we can pack more information into a qubit than you can pack into a classical bit. So considering that these are so what are these a and b? So say I measure for example, I measure this particular quantum state 100 times. 50 times I see that it is 0, 50 times I see that it is 1. So this means that the probability of getting 0 and 1 are equal, but both are non-zero. So this probability is what translates as these coefficients. So that's why it's called as a probability amplitude. And when we say that a qubit can exist in both, it exists in a superposition of, say, both 0 and 1. It is not a mystical thing where, like you are kind of spinning a coin and it is just like, caught up in an intermediate state. Mathematically, it is a real thing where it means that if you see a superposition, it translates to the fact that if you measure that state 100 times, half the time you will see 0 and half the time you will see 1. So that is what it actually means. So so one thing to keep in mind is that when you measure, you will never see a superposition as the outcome. You will never see it. Outcome is always going to be 0 or 1. But when you do the measurement and you see that half the time it was 0 and half the time it was 1, you infer that the state that you measured was in a superposition. So this is a very important sort of fundamental thing about quantum computing to keep in mind. So what can we do in quantum computing on qubits? You can of course do the same thing that you do on classical bits, like apply an X gate. So X gate is same as the NOT gate that we have in classical computing. So if you implement an X gate on a state 0, then you flip the qubit, and from 0 it goes to 1. So if you enact X upon 0, it goes to 1. If you enact X upon 1, it goes to 0. So how do we know this? Say if a qubit is in state 0, I apply X gate, it will flip to 1, but do I know it is 1? Not yet. I have to do the measurement. When I do the measurement, I will see that approximately the probability of getting 0 is 1, but the probability of getting 1 is like very high. So how do we know this? So if I do the measurement 100 times, 2 times I might observe 0, 98 times I will observe 1. So this kind of helps us infer that most of the state probability is concentrated on 1, and the state that was actually there here is 1. So the X gate has flipped the state from 0. So it's not yeah, that is because that is the way it is in nature, right? So if you want to observe that, you have to do infinite shots. Yeah, it is 1 only. So it is 1, but there are multiple things that can happen. So when I'm doing the measurement, when I'm doing the readout, there can be some readout error which is causing the 2%. But even more than that, the real thing is that if you want to like have 100%, like one has 100% certainty, you need to do an infinite number of trials. So only when you do an infinite number of trials, it will purely converge to 1. But it's always slightly, that there's that asymptotic, it will be approaching 1 like very, very fast, but it may never exactly be 1. So this is the consequence of, say, doing real experiments on a real quantum computer. So, but be rest assured that it is also possible that in very rare case we may get 0 and like we may get 100% probability in 1 also, which is the most accurate thing. But if you think about it, initializing this 0 perfectly, applying this X perfectly, then the evolution happening without any external noise affecting it, and this, sorry? Yeah. So if we do this, so if you do this in a simulator, even the simulator is based on a random number, this thing, right? So one other very special quality of a quantum computer is that it has inherent randomness, that inherent indeterminism that I said. So say for example, you are using a random number generator which is out of a classical computer, right? It is actually a pseudo random number generator. There is some logic. It's just that it's going to appear random enough to us. But in the case of quantum computing, this randomness is genuine. So you can really, so I can do this experiment, say 1 million times, and the 9,999th time, just because I got a 1 again, doesn't guarantee that the 1 millionth time I do the trial, I will get one with 100% probability, just because all previous trials have been 1. It is very much possible with 50% probability it can go to 0, it can come to 1. That inherent thing is that randomness is there. So this is again a quality of quantum computers that is not seen in classical, and some people try to, this is one of the qualities that can be harnessed as an application of quantum computing. So say I want to simulate some natural systems that appear in nature which have some inherent randomness, say some chaotic systems. So these kind of applications you can actually explore, because in quantum computers you can better encode that randomness as you can in classical computers. In classical computers, when you call a random number, it is not really a random number, it is a pseudo random number, right? But in quantum computing, that's not the case. You can see some genuine randomness here. So does that answer your question? So yeah, so let us proceed. So while it can do the same kind of classical operations, it can also do something that's different from what a classical computer can do. So if you look at the effect of the Hadamard gate on Ket0, this Hadamard gate is something that is capable of creating a superposition. So it takes from state 0. So you start with a state 0. When the Hadamard acts upon it, so just one second, let me go to the previous slide. So if you see here, if you look at the general state, how does that evolve? When you act the x upon this general state A0 plus B1, it flips the amplitudes or the probability amplitudes of each of the states. So Ket0 becomes, since A Ket0 has become Ket1, the probability of Ket1 becomes A and probability of Ket0 becomes B. So you kind of see an exchange of probability amplitudes when you enact X gate upon a general quantum state in the form of A0 plus B1, right? So now in the case of the Hadamard gate, if you start with a 0 state, then what does the Hadamard do? It takes you to a unique state, which is 1 by root 2 Ket0 plus 1 by root 2 Ket1. So this state is what is called as the plus state, which, oh my god, I think I will use my fingers, maybe. So this state is called as the plus state. And so why is it going to this particular state? That is because of the matrix that is Hadamard. I think it is, I'm not sure, but it is 1 by root 2, 1 by root 2, minus 1 by root 2, and 1 by root 2. So this is the matrix or the operator which represents the Hadamard gate. So when you enact it upon 0 state, which is nothing but 1 0, this is the state you will get. You can decompose it as 1 by root 2 1 0 plus 1 by root 2 . You can decompose it this way. So that's why it's in this notation, right? 1 by root 2 Ket0 plus, I'll just put it like this, Ket1, and this is called as the plus state. So similarly, say if I had state Ket1 over here, right? Say if I had state Ket1 over here, then if I had 1 over here and if I enact Hadamard, it will give me the state 1 by root 2 ket 0 minus 1 by root 2 ket 1. And this state we represent as ket minus. So, so if you see here, initially this was a pure state. It only had ket 0 or it only had ket 1. But when I put the Hadamard, it was able to create a state which has both ket 0 and ket 1 with non-zero probabilities. So when I measure this, whether I have plus or whether I have minus, I will actually observe 50% 0, 50% 1 in both cases. You cannot really differentiate on the first go whether you had a 0 state or a 1 state, because plus state and minus state, when you do the measurement, they will look very similar, because you're going to see 50% here and 50% there. So the one thing to keep in mind is that this the action of this H gate, so this plus and minus states, so there is something called as a computational basis in quantum computing. What does that what does a basis mean? So I said that you can represent any general quantum state psi, and I mean Arya also mentioned, discussed this a lot, but so any general state psi I can represent as psi A0 plus B1, where mod A square plus mod B square, oh, it should be outside. Mod B square is equal to 1. So this is called as the computational basis, which corresponds to the Z poly matrix actually. But the ket 0 and ket 1, these are called as the computational basis, and using these two states I can represent any general quantum state. But I can also use this plus and minus state to represent any general quantum state, and this is called as the Hadamard basis. So what this means is that I can any and all states which are contained within this block sphere can be represented using some coefficient of A and B in front of Z ket 0 and ket 1, and similarly with some coefficient alpha and beta in front of ket plus and ket minus, I can represent any quantum state. And yeah, so this is in some sense, if you apply a Hadamard gate because of this on any state, I mean if you are using the Hadamard gate, you can switch from the computational basis to this Hadamard basis in some sense. That's why it's called as the Hadamard basis. Yes, yeah, okay. Yeah, so I showed that here. This is so okay. Oh, sorry, I need to write this in a different way. This is more of a arrow rather than an equal to. So, oh, sorry. So this is the Hadamard gate, and when I do H say upon ket 0, this is the state. This is the state that I will get 1 by root 2 ket 0 plus 1 by 1 by root 2 ket 1, which is represented at plus, and this state is nothing but 1 by root 2, and I have 1 and 1 here. So 0 is just, so this is nothing but this matrix 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root 2, acting upon the vector 1, 0. That yields this plus state. Sorry, I've written it very shabbily, but I hope it makes sense. I can erase and rewrite if you want, but I hope it's fine. So that will, this matrix multiplication will yield this state. So that is represented by plus, and that is also all this. Yeah, so for ket minus will be, yes, this will be 1 by root 2, 1 minus 1. Yeah? So, sorry madam, in what is used in quantum cryptography? I'll come there. I can't hear you quite well. Yeah, Hadamard gates. So Hadamard, where are Hadamard gates used? They are usually used to create superpositions, and actually you will see Hadamard gates used as the first step in lot of quantum algorithms. because especially like they say examples like Grover. So what a Hadamard will do is, in this case, in the single qubit case, it put the state in an equal superposition where both ket0 and ket1 are available at equal probability, right? So now the magic is that any gate I implement on this state after just implementing the Hadamard, it will come upon 0, but at the same time it will also come upon 1. So simultaneous processing, if you think about that, I can simultaneously enact any operation on 0 that I am also enacting on 1, but not do it in two different steps. In a single step, I can process something that is represented by 0 and something that is represented by 1 parallelly, right? So in multi-qubit systems, so if I have, instead of just 1 qubit, if I have 10 qubits, in that case also, if I implement a Hadamard gate on all the 10 qubits, it will put the system in an equal superposition where each and every possible state will be present with an equal probability. So this is very useful, as I said, because you can, after that, any operator you implement will be implemented on all possible states at the same time. So that is very useful for, say, constructing algorithms and yeah, whatever you want to do. But the Hadamard is special in the sense that it can create a superposition, and this does not exist as a concept in classical computing. But a short answer to your question, madam, is that yes, it can, so if you're thinking about, it depends on what algorithm or protocol that is being used, but you will see Hadamard used to create Bell states, which is used in quantum communication and teleportation protocols. So it can be used. Yeah, you will see it in image processing cases. It is possible. It depends on what kind of algorithm you're using and what you're trying to do to your quantum state. So it can be used in any of these places. So some essential ideas. So now let us move to the next slide. So some essential ideas from quantum computing, for quantum computing that come from quantum mechanics. I'm not going to go too much into detail. Aryav has already discussed all this, but this is the block sphere representation that we were talking about. So any general state psi you have, it will be part of the block sphere, and you have these angles theta and phi. So first concept to keep in mind is superposition. So superposition is creating a quantum state that is a combination of both ket0 and ket1. So a general state, as I said, can be written as A ket0 plus B ket1, and these conditions allow us to map the qubit onto the block sphere. So if A and B are non-zero, then it contains both ket0 and ket1 with non-zero probability. So when people say that, a qubit can be both 0 and 1 at the same time, it's not some kind of mystical thing. It is mathematically this particular property. That means that they are in a superposition. Next, I need to change. So next essential non-negotiable idea from quantum mechanics in quantum computing is measurement. In quantum computing, if you want to probe the state of your system, you have to do a measurement, and a single measurement is not enough. You need to do measurement multiple times, and you need to be and there is more nuance to this. You cannot measure it too less. You shouldn't measure. If you measure too much more than needed, you might be losing the efficiency you get from using a quantum computing protocol. So the measurement must be done sufficiently enough number of times to balance between getting the overall state that you're looking for, but also without you losing out on the efficiency that you wanted to get out of using, say, a quantum computing methodology. So what does a measurement do? If your state is in if your quantum system is in a general state A ket0 plus B ket1, then by measuring it, we observe it, and by mod A square will be the probability with which we will get kept 0 when we measure, and mod B square is the probability with which we will get ket1 when we do the measurement. So for example, if I have this kind of state, this is nothing but the plus state or the plus state of the uniform superposition which we get. This has an equal probability of becoming both ket0 and ket1. Whereas if you have a state like this, root 3 by 2 ket0 minus 1 by 2 I ket1. So one thing to note is that these A and B coefficients are complex. They are not real. They are not just rational or real numbers. They are complex numbers, which is part of why we have a sphere and not a circle actually. So you have an extra plane where the numbers can be beyond just the real possibilities that you have. But this state means that there is a 75% chance of this becoming ket 0 and 25% ket 1. Then the very well known kind of almost sci-fi context entanglement that everybody must have heard of about quantum computing. What really is it? So in the case of single qubit, we saw that a general state is A ket 0 plus B ket 1. So suppose we have a 2 qubit system. A general state will look like this. You have A ket 0 0 plus B ket 0 1 plus C ket 1 0 plus D ket 1 1, where ket 0 1 means the first qubit is 0 and the second qubit is ket 1. And A, B, C, D are complex numbers, and even here the normalization criteria should be met. What does this actually mean? This means that when I measure the system, I will definitely measure either ket 0 0 or ket 0 1 or ket 1 0 or ket 1 1. When I measure the state of the system, it has to collapse to one of these states. So that is why when you add all their probability amplitudes, the square of them, it should sum to 1, right? So now if 2 or more of this A, B, C, D are non-zero and we cannot separate the qubits, they are said to be entangled and they are no longer independent. What do we mean by this? Let us look at it in a little bit more detail. So if I have this state where this is nothing but 1 by root 2 ket 0 0 plus 1 by root 2 ket 0 1. So here, if you see here, the first state is 0, the second state is also 0. I can actually express this state as 1 by root 2 ket 0 tensor product ket, or specifically like this. Oh, why am I looking for the yeah, let me write it instead like this. Let ket 0 does this state look familiar? We just discussed this. This is nothing but ket 0 tensor product the plus state. This is 1 by root 2. Let me write it like this instead. Is there a way to reduce the... So this is nothing but the plus state, right? So I can write this as ket 0 tensor product plus state. So this is not said to be entangled. Why? Because I was able to separate these two states. So say if I had something like plus tensor product plus. Now you can expand this state and see what it looks like. But I can have many possibilities. I can have minus tensor product. It doesn't have to be a perfect plus or minus state. I can even have something like say I can have tensor product 3 by 5 ket 0 plus 4 by 5 ket 1. I can have something like this as well. This is still not entangled. But if you look at this state, there is no way absolutely that, oh, what happened? I'm sorry, I think the annotations disappeared. But anyway, if you look at this state, there is no way you can separate it into some kind of a tensor product. Same with this state. So this is actually a Bell state. If you look closely, this is the 5 plus state. This is the 5 plus state, where you have 1 by root 2 ket 0 0 plus ket 1 1. This is the state that you will see used in a lot of quantum communication protocols, teleportation and the like. Because why is this state special? So if I know that I have entangled my qubits and this is the state that should be, say I take my first qubit, like I'm just measuring the first qubit, and say these two qubits are correlated somehow, in the sense they are a single system, but they are not close by in proximity, and say they are kept at very far. Okay, I measure just the first qubit and I see that it is coming out to be 0. So what is the state of the other qubit? I don't even have to measure it. I already know just by measuring this one that that should also be 0. Why? Because that is the only possible state here, right? So instead of 0, if I get 1, then automatically I know that the other state should also be 1, because that's how the state is constructed, right? So that's why this is a special kind of state that can be used in things like quantum teleportation and the like. But what is important to note is that this has entanglement. This state also has entanglement. Mathematically, entanglement means you cannot separate the two states. That is what is entanglement. Aside from what we see in movies like Avengers, like Endgame and all that. So this is what entanglement is mathematically. So before we go further, let us understand what is the state of the technology, that is quantum computing. So where are we today? So if you look at where we are, I would say that we are in the utility era. So in 2023, before 2023, I would say it was more pre-utility, where we had very noisy circuits available, and you could brute force all your quantum circuits to run on classical hardware. You really absolutely didn't need a quantum computer to just demonstrate or in some sense do qualitative quantum computing. But in 2023, we had a breakthrough which led us to see that we are now able to we are able to do computations that are beyond the regime of classical computing, even in the presence of noise. So so in 2023, this led to what we call as the utility era. And now we are able to do quantum computing, which is useful using techniques such as error mitigation, even in the presence of noise and without like completely having fault tolerant quantum computers. So in 2023, we were able to go up to 3002 qubit gates. But in 2024, we reached the 5002 qubit gates mark and we have up to 156 very high quality qubits that can do that are present on systems. And in 2029, we hope to bring out fault tolerant quantum computers with error connection enabled. So so this is the regime where today's well-known quantum algorithms like Grover, Shor's will really become powerful, quantum phase estimation. So until we get here, these algorithms are a bit difficult to implement due to various practical limitations, which we will discuss a little bit further during the lecture. So little bit about the IBM quantum roadmap. Just the key highlights I would say. What are the two main aims that we are hoping to achieve? In 2026, we hope to demonstrate quantum advantage before fault tolerance via quantum-centric supercomputing. Now, what do we mean by this? We will see why or what led to this, but the whole idea of computing is heterogeneous right now. So nobody is thinking that I'm going to run my algorithm from start to finish on a classical computer or on a quantum computer. We want to use different units of computing, say a quantum computer, a supercomputer, some HPC hardware. We want to use each of these components for what they can do well. So you design algorithms where you do part of the work on a classical computer, part of the work on a quantum computer, etc. And through this means we want to show that we can show some advantage via runtime or better, more accurate results, or some means we want to show some kind of advantage. And that is the whole idea of quantum centric supercomputing, where you do supercomputing with a QPU unit in the whole pipeline. And we want to show that we can demonstrate quantum advantage even before reaching fault tolerance via this sort of heterogeneous computing method. And in 2029, we hope to have the first large-scale fault-tolerant quantum computer. So this is the roadmap, and these are all various, milestones along the way which we tick every year as we kind of come up with some of them. But one main thing to keep in mind is that there are two sort of tires to this. You have the innovation roadmap and the development roadmap. Why we have two of them? It's because when we are developing things in the development roadmap, we inevitably come across challenges where you cannot just go straight beyond. You need some kind of innovation, some research which leads to some kind of breakthrough, and then that allows you to kind of move further in this particular roadmap. So this was, I think, released in 2023 or 2024, and the idea is that as we move through different milestones in the innovation roadmap, they will float up and manifest as things in the development roadmap. And right now, the latest things that we have achieved are HPC quantum integration for the quantum centric supercomputing related milestones. And basically more in terms of hardware, we have more performant hardware which have scaled up qubits, but also allow for more error free implementations. So I will not go too much into details, but this contains a lot of the milestones that we have and hope to achieve. So let us discuss a little bit about quantum computing applications today that we can see. Yes. Yeah. Where? Yeah, sure. Here? Here? Okay. Hmm. Hmm. Yes, that is actually precisely what it means, in the sense that, say, if I only have up to say 20 qubit, a quantum computer that can have 20 qubits, right? So you can add more, CPU nodes or whatever, and you can somehow just try to, work through the implementation on, classical hardware. Are those students who want to attend this session or something, or like they can join in if they want? But anyway, are there students who? If they want to join, just ask them to join, and I hope. Huh? What should it be? It's 1 by root 3, I think, right? Yeah, W state. Yeah, yeah, I think this is it. So these are also specially entangled states. You cannot separate them. So you have different types of entangled states, but entanglement is more of a general concept where I cannot further reduce the state into some kind of products. But in the case of the state which we saw earlier, oh my god, I'm looking for a duster. But let me use blue. So say if I have a state that looks like this, right? This is a state I can separate. I can separate this as ket1 tensor product so this is nothing but ket1 tensor product plus state. So this doesn't have any entanglement in the system. Okay, so anyway, this state doesn't have any entanglement in its system, but the other state that I described before, that cannot be further broken down. So entanglement is more of a concept. Specifically, it's actually called as a quantum correlation. So entanglement is not the only quantum correlation. There are things like quantum discord, contextuality. So these are all properties which are special. So quantum correlations are thought to be, the underlying sort of physical underlying properties which make quantum systems special. So they are non-classical, and they are what somehow ultimately allow us to harness different properties of quantum systems that allow us to have more advantage as compared to classical systems. So the overarching umbrella term is quantum correlations. Entanglement is one of the quantum correlations. So again, entanglement is a concept, but the Bell state is a specific kind of quantum state which is prepared. Yes, all Bell states are entangled, that is correct. No, entanglement, so entanglement again is it's a concept, so it's a sort of property that quantum states can have. So all Bell states are entangled, but not all entangled states are Bell states. You have other type of entangled states as well.
So I have one more thing.
Yes, sir.
Like gates are X gate, H gate, like that.
Mm-hmm.
They are operators.
Yes.
So operating on zeros and ones and zeros and specific results.
Yes.
They are taken in terms of matrix. So how we have to know that matrix 0 is 0 1 or 0?
Hmm.
Escape is 1 by root 2, 1 by root 2, 1 by root 2,
Mm-hmm.
minus 1 by root 2.
Yeah.
How they have got that?
This is coming from quantum mechanics, right? So this is yeah, so like of course there are motivations why certain operations are special. Yeah, so that is more like a very quantum mechanics based question, but like I would pose the question you're asking in this way, right? So in classical computing, I know I have a zero, say I have a zero, and I want to turn it into a one. I know what operation I should put. I will put an X gate, right? I will put a NOT gate. So if I want to, and if I have a specific set of truth tables and I want to kind of, manipulate a specific set of operations in a particular way, I will assign one gate to it, right? Like, so that is how we work in like classical computing. So in quantum computing, you think about it like this. I have a general state. This is the block sphere, let us say. I have a general state phi or psi, and this is my ket 0 state, this is my ket 1 state. This is my ket 1 state. Now I want to manipulate these various, states in various ways. So there are special, states here also, which you can say. So plus minus, I think this is plus, I'm not sure, and this is like some I, get I or minus I don't remember that honestly. I have to go back refer. But so you have special states in all these places, right? So if I want to manipulate these states in a specific way, how do I do that? So that is the question we're asking. So I know I'm representing ket 0 as 1 0 and ket 1 is represented as 0 1, right? Now it's a matter of finding the correct matrix, and it's even more easier to for me to figure out the correct matrix. How? Because this is a sphere, I know that I can span this whole sphere if I do three kind of rotations. So if I say I make an Rx operation, an Ry operation, and an Rz operation, so rotation gates also exist. So I say Rx of theta 1, Rx, Ry of theta 2, and Rz of theta 3. And if I do rotations along all three planes, all three different planes, somehow I can go from any one state to another state that I want to reach, right? So now by taking the combination of these, I can come up with as many gates as I need, right? So like Hadamard and poly XYZ, they are special because they are taking special states. They correspond to certain symmetries or certain properties, and that is how we kind of come up with those gates. But this is, let's say, like at least a logic which explains it. It's difficult to answer why or how we came up with those, but this is something, this is more of a mathematical motivation to explain why we go about that. So if you, I have to myself go back to the quantum mechanics course and remember why Hadamard came out that way, the way it did, right? So then you can come up with some explanation, but mathematically motivating it, I would say this is an answer. So for Hadamard specifically, if I want to put a state in a uniform superposition, how would I do that? If I take this 0, ket 0, and I want a state which has equal probability of both 0 and 1, if I want to manipulate it that way, what's the matrix I need? What does that same matrix do to this ket 1 state? So if we think about that, like it motivates us to see why the structures are the way they are, if that makes sense. So is that okay? Okay, so proceeding further, now we discuss why. So what kind of problems should we do on quantum computers? Yeah? Yes, madam, we'll go into that. I am discussing that only right now. So there is a rich seam of problems that can be solved by classical and, sorry, that cannot be solved by classical and AI supercomputing and never will be. These are trillion-dollar problems that quantum computing was really sort of designed to solve. That was one of the inspirations of, aspirations that led to taking quantum computing as seriously as we do today. So you have like, so there is a complexity class that you can explore. Okay, so you have NP complete problems which are extremely hard and cannot be which are like there is a class of difficult problems called as NP complete problems. Under these problems, you also have a set of problems which are called as NP hard problems. So a lot of these NP hard problems are very difficult for classical computers to solve, but they're easy comparatively for quantum computers to solve. So, and in the intersection of this, you also have easy problems which can be solved in polynomial times using the existing quantum algorithms. So, existing classical algorithms. So, what is this, regime that we should explore? We should explore this quantum easy regime. That is where we have, that is where we'll see some use for us to work in. But even in this, not all problems are equally relevant. We want to solve solvable problems which are quantum easy, but also problems which are interesting. And more than interesting, we also want to solve timely problems which will have the most impact if we tackle them now using the existing quantum computers. So the effectiveness is there, but there is also sort of a cap from the capabilities of quantum computers. So quantum computers today are much more performant than they were, say, even 3 years ago. So in 2022, the kind of quantum computers we had and the ones that we have today, there is a huge difference. Like, this is a field that has been growing as exponentially as its qubits do, right? So we want to explore timely problems which are solvable today using the existing quantum computers we have. So the success of the field that you are exploring quantum computing for depends on showing value beyond what classical capabilities alone can achieve. So when to use a quantum computer, this is what we were discussing about that about, say, just simple arithmetic, right? You are not going to do simple arithmetic using a very sophisticated supercomputer. For that, you will just use a calculator at worst. So there are very easy problems for which you absolutely don't need a quantum computer, like, arithmetic or video games. You don't want to use a quantum computer for these things. But there are also very hard problems. Say, for example, you are trying to use Shor's algorithm, or you're trying to do some, to break some encryption, or you're using Grover's algorithm to search an unstructured database. These are still difficult to implement while demonstrating some value. Why? Because you need fault tolerant quantum computers for these algorithms to be very successful in their implementation. However, in this whole range, there is a sweet spot in between where the problems are difficult but not too hard. And you while moving in this regime, you also try to pick algorithms which work well in this regime. About that, we will see a little bit more with time. But so, what are some of the industries across which we can expect quantum computing to have some impact? So you have mainly 4 categories you can think. This is not an exhaustive list, but this is like a main sort of, these are some of the main areas you can think about. So you have chemistry and materials, you have optimization and search, you have machine learning AI, and you have numerical simulations. So these are some 4 topics, right? But these 4 topics have problems across these different industry sectors. You have aerospace, where you want to make high strength to weight materials for say building an airplane. Then you have wing ply composite design optimization. You want to design the wings of your aircraft or flying object in such a way that the flight is smooth, or like it's not such that it's aerodynamic, say. Then you have computational fluid dynamics for aircrafts and other flying objects. So that is, for example, in aerospace. That these are the kind of problems you can explore in aerospace. So similarly, you have automotive, you have chemicals, you have electronics and semiconductors, you have energy, financial services, and healthcare and life sciences is one of the main sectors. So the question that madam was asking about medical, where you can see quantum computing applications for medicine, you can say for drug discovery and drug design optimization, you can use, quantum computing is already being explored. It's not even that you can use, it's already being explored. You have mRNA and protein structure prediction, you have disease target and biomarker discovery. So these are some of the examples across healthcare and life sciences. But you have such applications across different sectors and fields. So some of the more well-known ones are portfolio optimization and fraud detection in financial services. You have clean energy related applications in the energy field across electronics and semiconductors, again, you have multi-domain simulation, placement routing optimization, but also better materials for, doing things in this sector. For chemicals, again, you have numerical simulation applications where you're looking for better materials. Same with automotive. Mm-hmm. That is a very good question. So, for example, if you take the protein structure prediction problem, right? So, there are so many ways. I have worked in protein structure prediction myself. So, there are so many ways you can formulate the problem, and depending on how you formulate the problem, you can use a different, algorithm to solve it. So, right now, VQA, QAOA, all these, okay, these are variational algorithms which I was planning to discuss today. So these algorithms are, for example, explored using for protein structure prediction. How? You take the energy, you know that if I want to predict the structure of a molecule, at its ground state, it will have the minimum energy. So I know that I can represent the energy of a system using something called as a Hamiltonian, which is something that can be made into an observable. And as such, if I have a Hamiltonian, VQ is an algorithm which helps you find the minimum eigenvalue of that particular Hamiltonian. And if I can encode my problem such that that minimum eigenvalue will correspond to some structural parameters of that, structural or geometric parameters of that molecule, I can kind of infer back the structure it should have. So by correlating all this, I can convert VQE application. I can use the VQE algorithm for solving a protein structure prediction problem to predict the protein structure, like using the logic that its energy should be minimum. But using a similar logic, you can also, for example, use Grover algorithm. How? So the way the protein structure prediction problem works, you can frame one of the ways you can sort of interpret or frame the problem is, if I add one more, say I am looking at a protein with different amino acid beads. So as it is, if I consider that the template structure of that molecule should be in a lattice, if I just add one more say at amino acid bead to it, the possible structures will keep increasing exponentially. If I have say 5 amino acid beads, I have say 4 to the power 5 structures possible. But if I add one more bead, it will become 4 to the power 6. And if I add one more bead, it will become 4 to the power 7. So it's an exponential increase which you see. So you can also formulate this problem as a random walk, if I remember correctly. So you can make this a search of the correct structure which should correspond to the minimum eigenvalue. So you can potentially use Grover algorithm for solving the protein structure prediction question, for example. So it depends on how you formulate and how you encode the qubits, and essentially how you can translate these things effectively. That will tell what algorithm can be used for what logic. So ultimately, there's actually this framework called as a Qiskit patterns framework, which consists of 4 steps. And the first step is to map or encode your problem into quantum circuits and observables. So the way you do it, you can end up using different algorithms for evolving your state from problem to solution or input to output. So I mean I had to answer it a bit generically, but I hope at least gave you some idea. So yeah, if you think about it simply as an optimization problem, optimization means finding some minimum or maximum, right? And in the case of either Grover, it could be the search for a minimum eigenvalue, but for VQE, it will be finding the minimum eigenvalue by using the variational principle. So end result is same, the output we want is the same, but the method we follow is slightly different. Yes. And when one of the main algorithm related application studies that is done is about how you really adapt the technique, or how you adapt the problem well for a particular application, or how you adapt the quantum algorithm well for a particular application. So the kind of so the kind of interactions that model your say that model the energy that should be represented, say, by the Hamiltonian. There are multiple ways you can do this, and based on what algorithm you want to do or how you want to use a VQE. So VQE itself, for example, has a lot of variable parts. So there is something called as an ansatz. You can take multiple different types of ansatz to solve the same problem, and very good ansatz will give you a very good solution, possibly, if the other components are working well as well too. But yeah, so there are lots of different variations you can explore for different problems. The ansatz which works well for solving protein structure prediction problem well with VQE may not work equally well for a portfolio optimization problem which is being solved using VQE. Does that make sense? So you need to like adapt your algorithm well for the particular application you're doing. So that is also part of the game, that how am I adapting my algorithm well for my application. Yes. We are only through halfway of the halfway mark, but let's see. So just to get some consensus here, would you guys prefer this kind of a talk where we, so I'll tell you first what I have in mind for the rest of the session. So we will first explore some general applications of what happens, and how these applications are sort of designed with what logic in mind, and then we will have a sort of discussion about general discussion about algorithms which are difficult to implement today, and we will discuss VQE and why people started looking into VQE, or we can do a more hands-on session. Which would you prefer, like in the second half after the break? Mm-hmm. This one only. Okay. No, I'm asking, do you want hands-on or do you want me to finish this discussion? Yeah, okay. Sure. As such, I think the hands-on will also make more sense if we finish this, because you need to know VQE, understand how VQE is, what VQE is, to know how or why it is being implemented in a particular way. So yeah, like now and by 3:45 we will finish till here, and then after 3:45 we will discuss the algorithm part. If we have time, I will get started and just explain a very simple case of the hands-on. Okay, coming back to the session. Where were we? Okay, we were here. So now this is again a more generic representation of where you see example use cases, right? This is a very broad sort of overview. So some more, what kind of problems are really desired to be solved with quantum computing? So one of the subclasses of problems are structural problems, where you want to model molecules, atoms, electrons, quarks with very, very good accuracy. And why is this? First of all, forget the method. Before that, why is this even working in the first place? The initial idea of conception of why just quantum computers in general, how did it come? Where did it come from? So Richard Feynman first suggested the idea of quantum computers because he said, if you want to simulate a classic quantum system on a computer, so a lot of the computational studies we do, we try to model different systems to understand their behavior and predict what will happen, right, or predict some properties of that system. So if I want to do that for quantum systems, how am I going to do it? So it's the real reason why it's difficult to do it is because of the thing that I mentioned in the very beginning. Quantum systems have a quantum mechanical behavior, and that has an intrinsic indeterminacy in it, right? So there is some inherent randomness in it. And how will you use a classical computer which is determinate to represent that? It is not really possible. So he said, maybe a quantum computer which obeys the laws of quantum mechanics, that can maybe represent this kind of behavior better than a classical computer can. So that is why this is one of the foremost good applications of quantum computing, because there is inherent quantum mechanical nature in all these things, right? So if it has that inherent quantum mechanical nature, I can try to capture that, and ultimately somehow it works better on quantum computers. So you see a slightly higher degree of success for that. Of course, we are also using classical computers in combination, but the prime reason why quantum computers are working well for this is because it gels well with the inherent quantum mechanical behavior in some of these systems, right? So for this is an example of a state of the art application. So based on an algorithm called as sampling based quantum diagonalization. So using 77 qubits on a Heron quantum computer and some HPC architecture from the supercomputer Fugaku, we have been able to achieve results comparable with the best classical approximate methods for predicting the structure of this Fe4S4 molecule with in terms of accuracy and timing. So if you look at how much memory the classical exact method requires, and how much the approximate method requires, and how much the quantum method requires, you can just see the comparison of the resources here. So using 12 minutes on a quantum computer plus 1.5 hours of supercomputer time, we have been able to predict the structure of this molecule really well, as compared to 8 hours for a classical approximate method versus the classical exact method, which requires this much amount of memory, 63 pi b. So this is a huge amount of memory, right? So compared to that, we can already see the success of quantum centric supercomputing approaches and why these class of problems are good to be solved on quantum computers. So where else do we see this application? We see this in EV sector, where you want to energy sector, where you want to develop lighter, long-lasting batteries for electric vehicles, electronics, and energy grid storage. We also want to design lighter, stronger materials to allow planes and other aircrafts to be more efficient and need less maintenance. So for discovering new drugs, antibiotics, which can counter the emergence of multi-drug resistant bacterial strains. Then for designing optimal superconductors for say MRI, electromobility and renewable energies. So all these are in some sense, structure, understanding structure of molecules better. These are problems which deal with that. So quantum computers are a really good, so these problems are really good for as candidates to be solved on quantum computers. So nothing comes. So nothing comes off the top of the mind, but I can guarantee you that, like all the, big companies, Pfizer, there's one which starts with A, right? What's the one? AstraZeneca, yes, AstraZeneca. All of them are working on quantum computing applications as well, okay? And they're they're looking at, the docking mechanism, right? Enzyme, substrate, and this thing, what is it called? Substrate, the docking procedure. So that they kind of look at. Basically, if you look at diseases like Alzheimer's, what is the cause of that disease? What is the root cause of that disease? So if you see that, you will understand that a lot of diseases are caused by misfolded proteins. So proteins which should fold in a specific way are misfolding, and they're not the right shape. They're not the shape they should be, and this leads to disease. If you know about cancers like sickle cell anemia, where the hemoglobin is sickle shaped rather than the shape it should be. So misfolded proteins, all the root cause of several diseases is this sort of thing. Yeah, structural problems in the say the molecules. So to understand first what can be done to counter this, or to even understand these diseases better, this is a sort of materials research, right? Materials research problem where you're trying to find the structure of a molecule, why it is this way it is, or what is it. So yeah, so these type of problems, there are many applications, and BQE, for example, is an algorithm you can use to solve that. This latest algorithm is called as SQD, okay? So this algorithm has been used for a specific molecule. This is more of a chemistry application, but you can sort of generalize the idea to other molecules as well. So it's not a very specific answer, but I will suggest you do some kind of a literature survey. I am sure you will be able to figure out groups and research groups and, like, papers which have come out on this topic. So I wouldn't say that we are at a very highly successful level today, that we've done groundbreaking research using quantum computers, but every day we are finding out more efficient and, say, more promising ways to approach the problem which feels impossible to solve. Now the last breakthrough which came, let us say, was the AlphaFold AlphaFold product, which is AI based, but it was for protein structure prediction. But despite AlphaFold coming out, there are still a huge number of proteins for which we don't know the structure today, right? And that is actually a data based approach to finding out protein structure. It is not it does not work from first principles. It does not find the structure of proteins by saying, oh, so this is the kind of molecule, this is the kind of interactions they will have, hence this behavior should be that way. That's not how it predicts the protein structure. It will take the input of, say, hundreds of thousands of proteins. It will analyze the connections between the two. It will see, oh, so if this molecule sits this next to this one, it will correspond to this kind of bend or shape in the molecule. This is what the structural component is going to look like. So by ingesting so much of data, it will understand that, okay, if I have these kind of sequences connected together, this is the protein structure I predict it should have, and it's able to do that with a very high accuracy. But we don't have a very good pipeline from first principles to predict the structure of proteins and molecules. So a lot of quantum computing based approaches will do it from first principles. But in fact, you can even use the AI based, data based approach with quantum computers using some QML application. So there is a lot of room to play around with algorithms, approaches and problems. So it's a good thriving area of research in this field, I would say. So I hope that answered your question. Okay, so let's finish this and then we can go for a break. We are almost at time. But okay, the next set of problems which are really good to be solved on quantum computers. So if you remember, I said that you can squeeze in more data into a quantum system, into a quantum computer with a limited number of qubits as compared to classical cases, right? Just give me 1 minute, I'm almost done. Okay. So with the same as compared to what you can do in classical systems, right? So this also translates to the fact that quantum computing can, or quantum information based approaches can encode more complex correlations than classical systems can. So these more complex correlations, they translate into some hidden patterns which may not be immediately obvious with classical approaches. So this translates to problems where you can encode group symmetries and transformations of data. And because the language of the quantum, because quantum computers follow linear algebra and they can work in large spaces which are needed to answer difficult computational problems which can be inaccessible to classical methods, you see that quantum computing performs well in places where you have such hidden patterns in structured problems. So this translates to quantum computing being a good resource for solving optimization problems, for improving anomaly detection for rare events and, say, fraud detection in finance, for improving patient outcomes by designing optimal cell-centric therapeutics, then strengthening risk management through better time series prediction. And then you have logistic applications also, like optimizing vehicle routing and scheduling for large scale logistics networks. So these are some types of problems across different fields that can be good for quantum computing to be used as a resource. Of course, this is not exhaustive, but these are some examples which are easy to immediately understand and get started with. So let us finish the first part of the talk here. Any questions before we break? Yeah, hardware is actually going pretty well, I would say. We already have a 2029 this thing that we want to build a fault tolerant quantum computer, but I would say that compared to like earlier years, we have much better, very good hardware now comparatively with steady, uh, with very decent like error rates, I would say, in some sense. Why is because if you look at once this chip called as, so the first good chip was, I will say, Eagle, which had 127 qubits. But when we kept scaling up, we found that the quality is also a very important criteria, right? It doesn't make sense if you keep adding qubits if the overall computation is not having good fidelity or good quality, right? So the breakthrough came in the form of this tunable coupler, this in the form of this chip called as Heron, which initially had 133 qubits. Now it has up to 156 qubits. But this has something called as a tunable coupler, and what this does is it allows us to remove crosstalk almost completely from the systems. So crosstalk means if I have 10 qubits and if I operate something on the first qubit, something is unintentionally happening on the seventh qubit, which I don't want, and this messes up the whole computation. So by using this tunable coupler sort of technology, it has almost virtually almost eliminated all crosstalk, which you can see in quantum systems. And the other really good thing about the Heron chip is that this is the first modular chip which came out, meaning that when we are scaling up the number of qubits, we are not going to try and cram all the qubits into just one chip. We are going to have a chip which can be extended by adding, say, one more component of itself. So what we hope to do is, we hope to have one chip, then we hope to add like multiple chips together to make a bigger chip which will have more number of qubits. So this will allow us to help scale with not just number but also quality. So of course there are more optimizations for speed. So the main idea of building hardware, or the three main goals for building good hardware, at least with IBM, are three. You have speed, you have number, speed, and quality. So what did I say? Number, quality, and performance. So it's number, quality, and speed. These three criteria. So it must be performant as well. So all these criteria. So if I had gone through the roadmap, maybe it would have helped, but I'll leave that as an exercise to you, because there's a very nice video on the IBM Quantum website, and we have other things to discuss, but I'll leave that reference with you so that you will have a much more idea of what is coming up in hardware. In fact, we have even improved the kind of lattice that is there, so this will allow us to implement more gates, more gates, or basically it will reduce the depth of the circuits which were, so we have a new chip called as Nighthawk which is coming up, and that is based on square lattice instead of the traditional heavy hex lattice which was there in all previous chips. And this means that a circuit which had a moderately high depth in, say, like in the previous systems, will have much less depth in Nighthawk because of how it has been designed, because of the square lattice design. So yeah, I'll leave it at that. Yeah, the 10 minutes free part of the open plan has always been like 10 minutes only. At some point, no, it was 10 minutes. Now it is like, I mean, no, the 10 minutes thing has been there for quite a while. Like, it has not been more than that. Like, yeah, I have been using it myself for some time, and it has always been 10 minutes for free per month. Actually, it was free 10 minutes per month until before. Now it's 10 minutes, I think, for a rolling window of 28 days. So it depends only, like, the reset will happen based on how much you have used. And one thing is, now it is hosted in IBM Cloud. Before, the IBM Quantum platform was separate. Now it's hosted as part of Cloud. So you may have to enter your credit card information. This is for security verification purposes. So that might be a challenge for some people, but then it's part of the, like, so for general availability, you need to have certain robust security measures applied, so that you don't see like a lot of phishing attempts, or people unintentionally using your quantum computer for tasks they shouldn't do. So for all that verification purposes, through IBM Cloud, the protocol is that you have to enter a credit card number. So that is why it is. That could be a challenge, but that's how it is. You can actually use it now also. There's some skills build thing through which for 1 year you can get access, but after that you have to enter. So you will get some credit or some coupon code through which you don't have to temporarily enter your credit card information, but after 1 year that account will get deactivated. You have to enter that information at some point. So but you I will let you know. So it's via IBM skills build. You can look it up. Okay.
Basic elements of quantum computer, like in normal computer, we have like memory.
Yeah, so in a quantum computer, I mean, see, okay, some of it is like, say, of course, confidential, but in the quantum computer, like, okay, so this is an image of the quantum computer. This is the replica which was there at IBM, like Quantum Bangalore, in the Embassy Golf Links business park. So if you see, like, all this whole heavy fancy chandelier structure is just the refrigeration unit, right? So the actual chips are at the bottom in the hexagon, like the hexagon parts. These are the chips. So this is the refrigeration unit and these are the chips, and there is also going to be some other components which are there which interface with these chips so that it can, transmit and receive data. But that is as much as I can say. So some of this cooling, I'm not a hardware expert, but just to give you a qualitative idea, this is all the refrigeration unit, and down you have the chips, and like interfacing with that you have some electronic structures which will, receive and transmit data. So yeah, that's as far.
And all are part of this, or they are implemented somewhere in that.
The gates will be implemented via the chips. Yeah, of course. I did give a talk at some point on that, but it's been a while since since I kind of looked into that. So I'll maybe revisit it at some point, and maybe I can give you an answer after that. But even then, my answer will be limited because a lot of that this is intellectual property. You can see some, so some of this information will be publicly available, but not all of it. So yeah, I would but okay, one more thing I can say is that the unit of, so this is a superconducting qubit, right? Different types of qubits will work on different say photonic qubits will be fundamentally different from superconducting qubits. In superconducting qubits you have something called as Cooper pairs and Josephson junctions. So I will really refer you to look into what Josephson junctions are to understand better about how quantum computers work, because those are, that and Cooper pairs, they form sort of the main core idea behind how you form qubits, how you implement gates and the like. So yeah, there should be sufficient material on these two topics, so I would suggest you to look into that. Cooper pair. Yeah. Yeah, here. He's actually a material, like he has a materials background, so he should be able to answer that better than me. Yeah, no, now let's break for, yeah, we can break now. Sure.